and record.
Yeah, to
Okay,
get
so
this, I got a question. The
yeah,
study guides, I like to order them and have them in my hand. I like to have a book or a study guide in my hand, necessarily on a screen or anything like that. Where do I go get those, or where could I order them from?
the one that we're using,
Well, yeah, the ones we use in some of the tests.
the
Yeah,
tests.
yeah. I need to go ahead and work on some of those sample tests.
If you want to do sample tests on paper,
Uh, no, I can do them on screen, but
okay. But as
I'm
far
not
as
good, very good with the computer, and I just don't order much and stuff like that.
so right here, this is what we're using.
All right.
And notice it says you can purchase for 9.97 in print. Uh
Okay.
oh, sorry, take it back. Purchase a Kindle version or purchase a print version for 22 bucks.
Oh, I got you. Okay.
There's the print version.
Do
And
you have an HRO anywhere close to you, a ham radio outlet?
Portland. So
No.
that's 125 miles.
All y'all are, yeah, as I say, all y'all are southern
125 miles from here.
Oregon, aren't you?
Yeah.
That ain't bad. I'm 150 from my house right now.
Well, yeah, but you're getting paid. So
Scott, I hope it's okay. I have an extra member today in the class.
I see that. And what's that kitty cat tail's
We
name?
don't mind.
She is actually named for my favorite stage rally.
We don't mind.
Thank you. She's named for Ollie Cole.
Uh-oh. There we go. You dropped out when you were talking there.
Oh, sorry, her name is Ollie, named for my favorite stage rally road, Ollie Coleman Road.
Okay. And I used to have two cats named Otis and Otto. And my in-laws across the street have a dog named Oliver who I call Ollie. So
Aw.
yeah.
Yeah, we have 2 cats, 2 dogs, and 2 kids. So I believe that's called a full house.
That's a pretty full house. My daughter was telling me about somebody she works with recently, and let's see what that was. Here we go. 2 cats, 3 dogs, 7 snakes, and 12 geckos.
I think I'd have to pass on the snakes. The geckos are awesome. We did have 4 hamsters at one time.
Oh, I had one hamster, and I
Okay, I
learned.
have.
Go ahead.
Go ahead.
Oh, I had one hamster, and then the hamster had babies, and then I had one hamster again. I learned something about hamster. Oh.
I think I have all of you beat.
Uh-oh.
I've got 2 dogs, 1 cat, 4 blue and gold macaws, 6 400-gallon fish tanks,
Ooh.
3 of which are saltwater, 3 of which are freshwater. I have 2 Burmese pythons. I have 2 potbelly pigs. I have 4. I don't know what the heck they're called. Marmots
A
or
marmot?
marmots. Yeah, they're my daughters that I inherited when she went into the Air Force. And then yesterday afternoon, my 10-year-old came home with guinea pigs.
Hey. Just keep them away from the pythons.
Yeah.
No.
Oops.
So
Oops was her name, I think.
Yeah.
Yeah, growing up, we had a dog, and the most I can remember, we had outdoor cat. We lived on acreage. We had, I think, 20 cats at one time, but we didn't have any rodents or snakes or
Well,
anything.
yeah. So did anybody else see that I think it was Christmas Day at Portland Airport? somebody brought their two therapy llamas to the airport,
No.
and they were escorted around the airport and were greeting all the kids, and
That's pretty amazing. I
isn't
work
it?
in drug and treatment, alcohol treatment facility, and we ran into an issue where at one of the facilities I worked at that people were bringing dogs that were not, therapy dogs or whatnot.
Mm.
But when they started looking at it, the state law here in Texas actually accords that you can have a horse as your
Yeah.
therapy animal
Oh,
as well.
absolutely. Yeah. Yeah, but
So,
therapy llamas.
so I used to work in the ethics office of a Fortune 1 retail organization. Good luck. I think you can figure that out.
Uh-huh.
And we had a therapy skunk come into one of our facilities.
Well, so long as
We had a
it's
therapy
decented.
monkey. Yeah. We had a therapy monkey. We had a therapy boa constrictor,
Mm.
um, which the skunk and the boa constrictor would not be therapeutic for me. I would be in a panic state at that point, but the monkey was actually very helpful in the shopping process.
Well, yeah.
But yeah, and the scary thing about that is legally we could only ask one time, and if we asked more than once, we got sued.
Hmm. Okay.
Yeah. So yeah, there's a whole lot of legal ramifications around that and what you can and can't have in the building. Yeah.
There you go. Annette loves
So
boa
Texas, I
constrictors.
feel you down
Yeah.
there. Yeah.
All
Yeah.
right.
I do not.
Hey, whatever works. Hey, it's
Yep.
nine
I agree.
o'clock. It's 9 o'clock. Is everybody ready to get started? Everybody get a good night's sleep. And I actually drove up to Portland last night. So, and then drove back home at 11 o'clock. So it was a fun evening. So what does an active ham do on a fun evening between Christmas and New Year's? You go to a DX club meeting in Portland. Of course. Okay. Um, so today we are covering, and I'm going to share my screen. Today we are covering, I believe it is on page, it starts on page, it does, 35. Okay, we are starting on page 35, and 35 starts with radio wave characteristics. So we discussed what waves are, we discussed what radio frequencies are, and I think one thing that I'm going to do now is bring up once again the radio frequency spectrum, and then also show you guys where all of our stuff fits into that. So here's the electromagnetic spectrum. And let me unshare that and share this. Okay, everybody remember seeing that pretty picture? Notice all that stuff that has radio waves, and notice that we have frequencies and wavelengths. And we talked briefly about the fact that the speed of light is the common factor. You will notice that, for instance, toward the center of it, we have 300 megahertz, and it relates down below to that thing that says 1 meter. In free space, light waves travel at the speed of light. Radio waves travel at the speed of light. That's about 300 million meters per second. So what you will see is these multiples of 10, and there will always be a 3. The reason that exists is because if everybody remembers how yesterday we did that circle where we had E and I and R and P and I and E. So that's our pie chart, right? There's another one which is 300 F and lambda. Remembering that F is the frequency and lambda is the wavelength. And we usually say in meters. And this frequency is always specified in megahertz to use this formula. So the 300 represents the speed of light, because we said that V is equal to F lambda. And in this case, our V is replaced by the letter C, which is 300 million meters per second. And that's why we have the mega in here to take care of the millions. So what we now have is this formula, which is, again, 300 F and lambda. And we're just going to take a look at one of those, which was 300 megahertz. Okay, so we want to say, what is the wavelength? We don't know the wavelength, so we cross it out, and we're left with 300 divided by F, which is 300 divided by 300, which is 1 meter. So now what we're going to do is go back to this, and we will see that 300 megahertz is indeed, everybody, 1 meter.
1 meter.
1 meter. The
One.
reason that this is so important is that this is our interrelationship between the frequency we're using and the wavelength that it covers. So why is this important? Because this translates to an actual size of antennas that you would make. The same way that a pitch pipe, or the same way that a trumpet or a flute or an organ pipe is a particular length to make a particular note. An antenna of a certain length resonates on one particular frequency. So if you want to pick one particular frequency, you build your antenna to cover that frequency. Okay, so let's see. Back to this.
I can give you 2 quick examples of antennas if you wanted to show.
We'll get to it. I'm going to be drawing a lot. Okay, 2 components of a radio wave. Does everybody remember how to do the right-hand rule? Electric field, magnetic field, direction of motion, right? And they're all perpendicular to each other. So electric and magnetic fields are at right angles, and the travel direction is at right angles to all of those. Radio waves travel at the speed of light, which is 300 million meters per second. We're going to drill that into our heads over and over and over. So as the frequency increases, your wavelength gets smaller and smaller and smaller. We kind of covered that. Our frequency bands are noted by the approximate wavelength that we use. So now we're going to kind of put 2 and 2 together, and we're going to share this, which you guys already have. And notice that we have, for instance, 23 centimeters, which is 0.23 meters. And look at that. There's a whole bunch of frequencies that are available up there in that band. On the 6 meter band, it covers from 50 to 50.4. Well, 300 divided by 6 would be 50. So this one actually is at the very bottom edge of the band. So but it's, in some cases, for instance, 10 meters, that would be 30 megahertz. And you notice that it doesn't actually even show up inside the band, which covers 28 to 29.7. So it's not always exact, but it's approximate. And we call those that because it's a lot easier to say, I'll meet you on the 29.3 megahertz band. You just say, I'll meet you on 10 meters. The same thing is true with shortwave radio. Like the shortwave radio stations, there's a 31 meter band, a 49 meter band, a 60 meter band. And those are basically so that they call out general frequency bands. Okay, so let's go back to okay, we're going to go back to this. And okay, so these are 3 things that you're going to have to remember. HF, high frequency, VHF, very high frequency, and UHF, ultra high frequency. These different bands are going to, one of these, I guarantee, is going to be asked on your exam. And because remember, we noticed that there was a 10 times factor in every one of those. So 3 to 30 megahertz, 30 to 300, and 300 to 3000. This area is called HF. This is called VHF. This is called UHF. Now, does anyone remember where you'd find VHF and UHF channels.
Analog TV.
Analog TV, yes. Okay. Well, interestingly, you would think that these would actually be contiguous, but it turns out that another one of the things that I believe I sent you guys in the documentation was a band plan which was even bigger than the one that we just looked at. And let's see, open file location. Oh, there it is. Okay, so now I'm going to share this. Here we go. This is also in the packet that I sent you. And notice this is just in the United States, which for the most part matches frequency allocations in the world because radio frequency doesn't recognize international borders. It typically just travels across. These are separated out in, notice they're factors of 10, 3 kilohertz, 300, or this one's actually bigger, but 300 to 300 kilohertz. Then the next one starts at 3 megahertz, then 30 megahertz, then 300, and then 3 gigahertz, which is 3000 megahertz, then 30 gigahertz. And up here at 300 gigahertz is the practical end of radio where it turns into infrared. And in fact, look at that at the bottom. What do we have there? We have essentially a duplication of the thing that I sent you guys.
Roy G. Biv.
Hmm?
Is that Roy G. Biv?
Up here is Roy G. Biv, way up here in the between, right in here where it says visible. But all that stuff on the left-hand side where it says the radio spectrum magnified above, notice it is greatly magnified above, is it not? And notice all the different things that use radio. Notice all the different uses of the radio frequency spectrum. Those are all designated by colors, and you can see, like, let's look at just 400 megahertz, right flat, right at 400 megahertz. Radio navigation satellite, mobile satellite, standard frequency and time signal for satellites, meteorological aids, mobile, space resources, space operations, meteorological satellites, and so on and so forth. So now let's take a look at, for instance, 22 megahertz, a much lower frequency than 400. And you will see that that area is used for maritime mobile, aeronautical mobile, fixed, broadcasting, general mobile radio. There's a space research. These are very different applications, are they not? One of them had meteorological satellites, and the other one is land mobile, things like that. So the question is, why are they so different? That actually feeds into what we're talking about today. The reason that it does is now we're going to cover something called propagation. So we are on page 38. Propagation is the study of how radio waves travel through space and encounter things in their environment and react as a result. So all different radio waves have different wavelengths. Everyone agrees with that. Well, if I am a wave, for instance, and I am this big, and I encounter something that is this big, that's pretty significant, right? Now, if I'm a wave that has the same amplitude, but I'm this long, that obstacle doesn't really seem quite so big, does it? If I'm a really big, long radio wave, that obstacle seems kind of tiny. So different size objects behave differently when they interact with different wavelength radio waves, different frequencies. For instance, if I aim something at, if I take the curvature of the Earth, we know for the most part that unless something weird happens, light waves, light travels in straight lines. I think everyone agrees with that. However, so here's light. You typically don't see beyond the horizon. Now, radio waves, on the other hand, are an electromagnetic wave, just like light. but they will tend to hug the surface of the Earth a little bit. The longer the radio wave is, the smaller the Earth seems in comparison, and the more it will hug the surface of the Earth. And this is known as ground wave.
Are we going to be talking about skip also?
Oh, yeah. We're doing that in about 30 seconds. So this is known as ground wave. So the lower the frequency, the more the flatter the Earth looks, because the waves are just longer and longer compared to the curvature of the Earth. So light waves travel in very much straight lines. Radio waves can bend a little bit around the surface of the Earth. Now, that's along the surface of the Earth, but we also have this other aspect, which is the fact that, okay, well, the Earth is curved, but we also have this stuff going around the Earth, which is way up here. And this is really fortunate because this is where we live. Right? We lived way down at the surface. And there's me. But we're way down at the surface. But all this stuff is the atmosphere. So the atmosphere serves a couple of significant purposes. Number one, it has air, it has oxygen so we can breathe. So the atmosphere is roughly 21% oxygen and roughly 78% nitrogen. So that's 99% of the components of the atmosphere. The other stuff, that's carbon dioxide, that's methane, that's sulfur dioxide, all the other stuff. But for the most part, as far as we're concerned, it's that 99% oxygen and nitrogen that makes up the atmosphere. Now, the atmosphere also is very, very thick down here, and it gets thinner. Anyone who's ever flown in a plane, it gets thinner and thinner and thinner the higher you go. And so when we start to deal with atmospheric thickness, we start to deal with density of finding atoms. So at the very low altitudes, which is really fortunate, we have very dense atmosphere, which has lots of oxygen for us to breathe. Way up here at the top, we might encounter a few atoms per cubic meter. It's still atmosphere, but if you want to think of it this way, the further off you go into space, you basically get to the point where you have no atmosphere. There's an end of the atmosphere. Well, so all of these areas are very important to us, right? Well, the bottom area is really important because that's what we breathe, right? Otherwise, we wouldn't really survive very well. The top layers are just as important, however, because the sun doesn't just emit light. The sun, in addition to emitting light, emits ultraviolet and X-rays and infrared. And again, it spits out radio waves and it spits out visible light in the whole spectrum. Clearly, not all these things are good for us, right? Raise your hand if you like that it's light outside from the sun, right? Yeah, me too. Raise your hand if you're happy that the sun hits us with heat and the earth isn't a cold, dead ball. Okay, so that's good. The infrared and the visible light, we kind of like. Okay, well, the radio waves, the sun makes a lot of radio waves. And those don't really bother us. They're very long wavelength. However, how about these X-rays and ultraviolet? Does anyone enjoy getting a sunburn?
No.
No. Okay. And how about anyone if they were to get bombarded with 10 X-rays every day for their entire lives?
Pass.
Probably not, right? That would probably lead to the end of the human race. So we are very fortunate that we have the atmosphere, because what we end up with is the upper layers of the atmosphere, which are thankfully above where we are. What happens is that, in particular, ultraviolet and X rays get trapped in a way. So we have nitrogen and we have oxygen molecules floating around. They're O2 and N2. And the incident rays, the incident photons in the X-ray range, for instance, will very often collide with something in the upper atmosphere. What will happen is they'll have enough energy that they can actually take an electron and cause it to pop away from the parent atom, which leaves an oxygen molecule that has a positive charge or a nitrogen molecule that has a positive charge, and cause an electron to be ripped off from that. So what you end up with is you end up with a constant generation. And for instance, because the density is fairly low, eventually these free electrons, because they're just floating around, will eventually collide with a positively charged atom. They'll turn back into a neutral atom, and then it will no longer be a free electron, known as an ion, or the atom is the ion and the electron is an electron. This is continually happening during the day. So let's say that we have the sun started over here on the left-hand side, and it's been moving that way all day. So as the sun has been moving, so let's say in the morning, all the way on the left-hand side, where is the maximum amount of stuff in the atmosphere that is being converted into electrons and ions? It's in this range, right? How about way over here on the right-hand side before the sun has made its move across the sky? So what you end up with is you have a lot of electrons floating around here, but not over on the right-hand side. Now, as the sun makes its trip across the sky, and we know that the Earth is really just turning, but we're going to say that anyway. As the sun makes its trip across the sky, what we end up with is that the sun is no longer on the left-hand side. The sun is on the right-hand side. So all those atoms, all those ions and electrons that were made on the left-hand side, the sunlight's not so strong over there anymore, and they're eventually going to start recombining. So the electrons that were formed are going to recombine and just turn into neutral atoms again. So what happens is that the electron density on the right-hand side, because this is now in direct sunlight, you're going to start to have those forming. So you might still have a couple of them left over here, and these tend to be somewhat proportional to where the sun is shining. So now what we're going to do is we are going to make it nighttime. All right, so the sun is no longer shining. What happened to all those electrons that were made when it's nighttime? Are there any new ones being made?
On the other side of the Earth.
That's right, on the other side of the Earth. That's pretty far away. So what you end up with is you have an electron occasionally, and an electron occasionally, and an electron occasionally. So your density of electrons floating around goes down at night. They're formed during the day, and they disappear at night when they recombine. This actually happens at about 250 miles up. And this layer starts, the interesting part of it starts at about 100 miles up. And then there's another layer that starts at about 50 miles up. And this is known as the F layer. This is known as the E layer. And this is known as the D layer. So of these three layers, where do you think the overall density of stuff would be higher?
D layer.
D layer, because it's closer to the Earth's surface. All right. The D layer has this kind of a special effect during the day, which is when solar, let me make that the right color. Don't want to have a red sun. Don't want to look 5 billion years into the future. So we have all the solar radiation that's coming down. Some of the ultraviolet makes it down into the D layer. And what happens is that there's so much stuff down there that the ions tend to form. They get excited. There's a lot of activity. So this actually forms an absorptive layer for radio. So where does all this go? Okay, so what happens with radio waves is that a radio wave that is launched skyward encounters stuff, right? It encounters ions, it encounters atoms that are just there. It encounters electrons. And if any has anyone ever taken a spoon and stuck it into a glass and noticed that the spoon was bent? Has anyone ever done that? I hope so.
Oh yeah.
Okay.
Yep.
That happens because the index of refraction of water is different from air. And what it does is it changes the angles at which the light travels. Radio waves, because they're just another version of light, just a much longer wavelength, can do the same thing. So we take our radio wave and we aim it skyward. Here, we'll do orange. We'll aim it skyward. And when it gets to a cloud of electrons, the index of refraction changes. So what can happen is, well, if it's not too different, it can just shoot on through. If it's a little different, it can do this. If it's significantly different, it can do this. If it's really different, it can do this. What was that last one? What just happened to it?
Skip.
It's a sine wave.
Yeah, but what just happened to it? It got made it to that F layer up there, and what just happened to the wave?
It refracted.
It refracted, it got bent down, and by the time it gets back down to the earth, how far has it gone? The person who heard this is how far away?
250 miles.
That's about 2,000 miles on the high frequency bands. This is known as skip. This is an ionospheric propagation mode that utilizes the F layer of the atmosphere. Now, interestingly, the density of the electrons up there in the sky largely determines the frequency of the wavelength, the frequency of the wave, and thus the wavelength of the wave that can be bounced back down. The maximum frequency that gets bounced back down, because we are actually intending to do this, that is known as the MUF, or maximum usable frequency. The higher the density of electrons up here, the higher the maximum usable frequency. So when do you think the frequencies would be, the usable frequencies would be higher, during the day or during the night?
During the day?
During the day, because at nighttime, what happens?
There's not as much electron activity.
That's right. The electrons have recombined with their parent atoms, and your electron density goes down. So your frequencies that are usable go down. Now, what we have available to us is something that's a really cool tool. And the reason that it's a really cool tool is that it utilizes something called FT8, which is a digital mode. And this digital mode is such that people usually leave their radios on all the time, listening for other stations. So what we're going to do is we're going to pick, we're going to say sent by, and we're going to pick a grid square, which is a location on a map. We're going to go with JO65, which is in Germany. And I hope it's fast. I can't promise. It is a web page. So essentially, this is generated by an aggregation of all the signals that have been received from one point on the surface of the Earth, from all other points on the surface of the Earth. And notice, I'm sorry, it's still loading. And what this will hopefully show us when it finally finishes loading, if it finishes loading. Dun-dun-dun-dun. Still waiting. Still waiting. Okay. I'm just going to go away from this for a minute while I'm waiting for it to load. Ah, live TV, right? Huh. Anyway, the other thing that happens is that as we draw the Earth, what we end up with. Oh, it finally finished. Okay, I spoke too soon. Okay, here we go. Okay, so these are from certain spots on the globe, people that have been able to hear other stations. And one thing that is interesting about this map is notice that the light colors, like yellow, those represent higher frequencies. Higher frequencies require more sunlight. So notice that from Germany going west, we have a partially sunlit path. That means that the 20-meter band is actually getting propagation to much of the United States. However, how about to the east? There's a lot of Japanese stations out there. Where are they all?
In the dark.
In the dark. Those bands are not working right now to Japan. So let's look at another one. Let's go PM95. I hope this loads faster. So this is looking at Tokyo. I hope it loads quickly today. The goal of this is basically to show that different frequencies, because we're basically dealing with, a sunlit Earth that's half sunlit at any time, different frequencies travel different directions at any given time based on the physics that are created between the sun and the Earth. So if you didn't think you were getting into a space science class, I'm sorry, but there's actually a lot of space and atmospheric science involved in ham radio. And come on, it's still loading, kind of slow. Come on.
Patience is a virtue in this hobby.
Yeah, it is. Okay, well, while that's happening, as soon as I click off, it'll probably update.
A watched pot never boils.
That's right. Okay, so what we're going to do is we're going to take a look at okay, so here's the surface of the Earth again. We're going to go with D, E, and F1 and F2. Notice the F layer is actually drawn as F1 and F2. The reason that we do that is because it actually splits into two layers during the daytime, and then they recombine at night. The E layer is good for something called sporadic E propagation. The reason it's called sporadic E is that it's very hard to predict when it's going to happen because it's at a much lower altitude. Its skip zone, if it happens, is usually about 1,000 miles. The F layer, when you get skip off the F layer, can be up to 2,500 miles. So this D layer, what good does this D layer do? And everyone here, if you're over the age of, I'll say 25, you've probably experienced the D layer, even if you didn't know it. If you've ever listened to an AM radio in your car for any reason, and you've noticed that during the day you only hear the nearby stations, but at night you hear the faraway stations also, like in between the big ones. The reason is that during the day, the D layer builds up very heavily and becomes an absorptive layer for anything up to about 10 megahertz. Well, the AM radio band is at 0.5 to 1.7 megahertz. That is definitely lower than 10 megahertz. So during the daylight hours, those radio waves that are sent up into the atmosphere, even though they could make it up to this F layer, they never make it there because all the energy is absorbed in the D layer. The D layer is, again, very, very dense, which means that there's a lot of electrons and a lot of ions floating around. At night, because there are a lot of electrons and a lot of ions floating around, what happens is that this layer disappears right after sunset. And that becomes transparent. And now you no longer have the D layer to worry about. So right after sunset, that band, in this case, AM radio, on the ham band, the closest thing we have is 1.8 to 2.0 megahertz, which is known as the 160 meter band, goes long distance. And that's why you can hear stations from 1,000 miles away after dark on AM radio. So the next time you're in your car, if you still have an AM radio, you can listen to the difference between daytime and nighttime. That's also why AM radio stations, if you've ever been listening to an AM station for any reason, right around sunrise and sunset, sometimes you'll hear a pop as the station seems to go dark for like a quarter second. The reason that's happening is that, number one, they went from daytime to nighttime or nighttime to daytime power. The power limits are different based on where their propagation is going to be. And on top of that, it might be that there's a station over here and a station over here. And during the day, they can both be transmitting and not bother each other. But at night, they start to bother each other because they're within mutual communications range. So this station on the left might actually change its antenna pattern so that it transmits that way, and the one on the right transmits that way, so they don't interfere with each other. So there's a lot of there's a lot of stuff that goes on behind the scenes to make this whole system work. Okay, so let's go back and see if our page has loaded. Oh, look at that. Okay. Well, notice what we have. This is on the 40 meter band. When we were looking at Germany, we were looking at the 10 meter band, 20 meter band. This is the 40 meter band. All the bluish purple indicators. Everyone notice that that's the only band that seems to be there. Those are really long waves. That's the 40 meter band. That is a typically nighttime band. It's been, as the sun is basically moving from right to left on the screen. So the sun is about to come up. It just came up in Hawaii, and it'll come up in Japan in a couple of hours. So what that means is that in Japan, it's still dark. It's probably about 3 in the morning. The 40 meter band is active. Nothing else is active. And again, this is all aggregated by people who are on the digital modes. Their computers are continually receiving reports from other stations and hearing everybody from around the world, and then reporting it to a centralized server, which then puts it on this map. Very cool tool.
Is that D-Star?
This is PSK Reporter. D-Star it uses the internet. This is all long distance propagation using the ionosphere. There's no wires here, other than beyond the roof. This is each station is running a piece of software called WSJTX. That software is listening and logging everything that it hears and sending it all to a centralized server. So now let's take a look at where we are in Oregon, and notice we still have some of the blue because the sun hasn't been up for very long. But over in the daylight areas, we have these tan ones. That's the 15 meter band, and we also have a crazy number of, and I'm just going to bring up the pink ones if I can.
So
Come on.
Scott, what can you do with this information?
This tells you where to go
So where to go listen?
and where to go try to talk to someone if you want
Okay.
to. Okay, so like from the West Coast now, this is where we are being heard. Now, I want to point out to everybody this map of the United States. What is the most significant thing that you notice about this map? And it's not the huge number of stations that can hear the West Coast on the East Coast. What is the big thing that you notice about it?
It's in the sun.
Yeah, but well, even bigger.
It's a significant number of stations in the Midwest and East Coast and less on the West Coast.
And well, it's not only less on the West Coast. What do you notice? Everything between the West Coast and the Mississippi River.
There's not much.
It's gone. Why is it gone? This is geometry.
Position
Because
of
it's
skip.
flat.
The distance of the skip.
The distance of the skip, the angle at which waves are hitting the atmosphere would have to be too high. It would be too steep for that layer to curve them down. At some point, it gets steep enough that it goes this way.
So you can't play pool that well with radio waves.
Nope. That's exactly right. So
But
this
you also have terrain into this, don't you?
nah, not on these bands.
Okay.
You get those on local bands, you know, on ground wave and okay. But now, how about those paths to Europe? What do you notice about those paths to Europe?
They're farther north.
They basically go up and over the North Pole because that's actually a straight line. Anyone who has ever flown,
They're getting thinner, aren't they, too?
yeah, they're starting to thin out. But what do you notice about it? Kind of following the shadow.
The arc follows the shadow.
Yeah, this is actually known as the gray line between light and dark, and radio waves are really good at following along the gray line. The gray line is where the D layer starts to fade, and you start to have, you know, really interesting propagation characteristics. Now, we notice we also have what part of the planet would you expect that there is more ionization right now? If I were to draw the equator, would you expect that it would be north of the equator or south of the equator?
South.
That's right, because it's
Winter.
it's winter for the northern hemisphere. And in fact, during the summertime, this path from the Pacific Northwest to Europe that goes up and over the North Pole can be open 24 hours a day
Wow.
because the sun's always up 24 hours a day on the North Pole in the summertime. Similarly, even though it's a longer path, I have actually worked from the West Coast. I've worked stations in India going this way over the South Pole and then into India. The reason that works is because most of the path is lit up. Even though it's the 17,000 mile choice instead of the 7,000 mile choice, it's a better path because most of it is lit up. And on top of that, if you look at the map, most of it is also salt water. And what do we know about salt water?
It's a good conductor.
It's a good conductor. And a flat, salty ocean makes a very good reflector for radio waves. So paths that go over salt water are really, really good. Now, the other question, of course, I have is some of those paths, for instance, here's the Earth again. Some of those paths will be here to here. Well, that's clearly more than 2,500 miles. 2,500 miles would be about here. Another 2,500 miles would be about there. So how is that path working?
Is it relaying off of other towers?
There are no
Or
towers.
antennas?
There are no towers, no antennas.
Belts.
Multiple skip. So what that means is that everywhere along that path, there has to be good propagation for that particular frequency. So if we were to look at, for instance, this map again, and I'm sorry that I spend a lot of time on this, but to me, this is one of the more interesting and important parts of what we're doing.
You're not even touching on every aspect of it.
Oh, no, of course not. So what we're going to do is we're going to go to azimuthal equidistant. And this should change the map, I hope. Maybe. Come on. Come on. I want it to be an azimuthal map as opposed to the Mercator. I'm telling it to go. I probably have to tell it where to go. We'll see if it works. Okay. So anyway, while that's loading, what can I say? They've gotten what, 2 billion hits with propagation. Oh, there we go. Now, of course, it opened up. Okay. Here we go. Here's another view of that same map. And notice what we have, daylight versus nighttime. It's really pronounced, right? And so now if I were to take a look at from, let's say, the Pacific Northwest to India, notice it goes kind of northwest and it's a mostly dark path. But if I go toward the south, I go over Antarctica, that's all lit up. And just the end of that path has to go over darkness. So that actually is a much better path. So now the question is, since India going the long way is 17,000 miles away, how many skips have to work in coordination with each other for that to work? Approximately at 2,500 miles each to go 17,000 miles. Approximate number.
Seven.
Like 7 or 8.
Seven
Yeah,
or
it's
8
7.
skips have to all line up, and the maximum usable frequencies and everything have to work out along the entire path for that to work. That's why it's not always a reliable path, because everything has to line up just right. Right. I've done it a couple of times because I've been there and the conditions were right, but you can't rely on it typically. But it's certainly amazing when it happens, because it's something that, really shouldn't happen, but occasionally it does.
Hey, Scott, so that brings my curiosity level out. Can I ask you a question about a certain station?
Sure.
So there was an antenna once upon a time, I believe it was in Belgium, that was, I think, 1,000 foot tall or something like that.
Mm-hmm.
Back in the day when my grandfather was on ham, we used to be able to hear that station. Was that an effect of skip, or was that because their antenna was the biggest thing on Earth
Combination
until they built the Burj Khalifa?
Combination of the two.
Okay.
I mean, getting up high means that you can have a low launch angle with regard to the horizon. That's why people like to build antennas at high places. I mean, because your launch angle to the horizon is nice and low. Now, it's more pronounced when you're talking about VHF and UHF, because things like hilltops, they're right in the way, because you're basically scraping along the surface of the Earth. So, like, for instance, okay, right now, radio horizon for VHF and UHF, we covered that. Why are simplex UHF signals rarely heard beyond the radio horizon? Because they're not propagated by the ionosphere. Their frequency is way too high. Since they're not propagated by the ionosphere, they're really good for talking to satellites. VHF and UHF are frequently used for talking to satellites. So let me ask, that 1,000-foot tower, if it had a VHF antenna pointed at Oregon or Arizona from Belgium, would it ever make it here if it was on VHF?
No,
No.
No, because that's line of sight. So
Yeah, I was gonna say no because it's an ultra high frequency. You'd have a better shot at the AM bands
Correct.
getting here than you would anything FM.
correct. Now, for those of you who know Oregon geography, I have been in Eugene on a handheld radio and actually been able to hear somebody in Portland on a hilltop. We have a guy who went to Crater Lake and using a handheld radio was able to get in contact with our repeater station, which is at 3,500 feet. Crater Lake is at 8,000 feet, using a handheld radio covering a distance of about 200 miles, just using a handheld radio. So the question then that people ask, which I hate this question, is, well, is this a long range handheld radio? Like, well, it depends. It depends on a lot of things. So do you normally think of a handheld radio covering a distance of 200 miles? I don't. But, I've used a hand I yeah, I've used a handheld radio with a 3-element antenna to actually talk to an astronaut on the International Space Station. That was 220 miles straight up. But when I talked with him, it was probably a distance of about 300, 400 miles because of the angle that I was working him at. That was just 5 watts on a handheld radio with a small with a small Yagi antenna. So it totally depends. Why do VHF signal strength sometimes vary greatly when the antenna is moved a few feet? Well, we're going to draw a little diagram here that will hopefully make this make sense. So here is our direct path between point A and point B. And now, because we know what waves are, we're going to act.
You've lost your audio, Scott.
I lost my audio. Okay, there we go. Better?
Better.
Yeah, okay. I disconnected myself. Okay, so we're doing multipath. Okay, so what we're going to cover right now is we're going to make point A and point B exactly 3 wavelengths apart. It doesn't have to be 3. It could be 1. It could be a billion. It really doesn't matter. But what's important here is that we're going to draw another wave which is generated by the same wave, except that, our radio waves travel off in all kinds of directions, right? Well, since our radio waves travel off in all kinds of directions, I mean, there's no such thing as a perfectly focused beam. We're going to take one of our waves, which is fortunate enough to go this way. When it gets to a certain point, it hits a rock and bounces off that rock and ends up at point B. Which, because the 2 waves are generated at the same time, which one gets there first? The green one or the red one?
Red one.
I hope not. They're made at the same time.
The one traveling the shorter distance.
That's right. The straight line is going to get there first. So what that means is that, remember we mentioned something called phase? Phase is a measure of the delay or advancement of one wave compared to another wave. Right? Okay, now waves also have, so they have phase and they also have their size, which is known as amplitude. Amplitude is basically just how big it is. Think amplification. So we have our phase and our amplitude. Okay, so what can you say about the amplitude of those 2 waves that I drew, the red one and the green one? Are they going to be the same? Yeah, probably not, right? You don't know for sure. I mean, maybe it's a really good reflector. Maybe it's not. I can't say. But now what can you say about the phase of those 2 waves? When they both get there, The green one is going to basically get there like this. What's going to happen to the red one? It took longer to get there, right?
Is it going to be weaker?
It's
It
going to
might
be out of phase.
It's going to be out of phase. So this can do a couple of different things. When two signals get to one point at the same time, they add. So if they are perfectly in phase with each other, you'll basically have this. If they add, what do you end up with?
Stronger signal.
You end up with a bigger wave. Yeah, exactly. You end up with a stronger signal. But what if they are perfectly out of phase? What happens if you add those together?
They get choppy.
They cancel each other out. Every
Okay.
every part adds to the other one, and they're equal and opposite. This is phase shifted by 180 degrees, which is a complete cancellation if the amplitudes are the same. So what ends up happening here is that you end up with a situation where if you have multipath, where you have waves that are traveling different distances because they are traveling in different directions and hitting different things, you will have your initial one that looks like this. You'll have some that are, let's say, this big and delayed a certain amount. You might have another one that is delayed by this amount, which is bigger. They're all at the same frequency. They're all at the same wavelength. They're all going from point A to point B, but the green one got there fastest, the red one got there a little slower, and the orange one got there slower. What's going to happen when they all get there? I have no idea. You're going to get some addition and some cancellation. So you're going to end up with something that is called constructive interference, which is when things add together, and destructive interference, which is when they cancel. So what if I were to now take these signals and I were to physically move myself so that point B is now in a different location? And I went from a situation where this was no good, NG, because I had cancellation. I'm going to erase those. And now I'm going to leave the rock there because I can't move the darn rock. But what I can do is I can say, okay, well, I'm going to draw a line from A to B. But now this path from A to B bouncing off the rock is so that it actually gets there in phase, delayed by one wave, because this one had 3 wavelengths. This one had 4 wavelengths, but they got there and they were in phase with each other. All I've done is move myself a little bit that way, right? But what I've done is I've changed the path lengths that those waves had to cover. If you have a handheld radio and you are listening to another station, let's say that I ended up having to move a half of a wave. To make this path length make a difference. If I am on the 2-meter band, which is roughly 146 megahertz, we are going to take a look at that formula 300 F and lambda. And our frequency is 146. So what's 300 divided by 146, everyone? Roughly?
1.2.
It's 2 meters. That's why we call it the 2-meter band. So what does that mean if I had to move a half of a wavelength to make this signal readable? How much is a half of a wavelength if my wavelength is 2 meters?
1 meter.
1 meter. 1 meter is about 3 feet. So I took my handheld radio and I moved it 3 feet, and the station that I was listening to went from really weak to really strong. That's physics. There's no way around it. However, you can also use it to your benefit, right? We just did. If you're on the 70 centimeter band, which is 440 megahertz, and you move a half of a wavelength, how much is that? That's about 1 foot. You move your antenna 1 foot, and it goes from being weak to really strong. But now let's just add one more rub to this. Let's say that instead you are in a moving car. Trust me, you will be in a moving car if you do this, and you're moving in some direction, which causes path lengths to continually change. And let's say you're driving down the highway and there are trucks and things like that. And this truck is moving that direction and you're moving this way, you're at some intersection. What's going to happen as these continually make and break, if you want to think of it that way? This is known as picket fencing. And the reason it's called picket fencing is that if you can imagine trying to talk to somebody through pickets in a picket fence, where you have a clear path and then all of a sudden it's blocked and then it's open again and then it's blocked, it will actually literally sound like that as the stations are moving. And that's known as picket fencing. And again, completely a result of physics. If you're using digital communications, for instance, multipath propagation will tend to increase your error rates, because when your signal is not a single signal, you're going to have cancellation. Cancellation reduces signal strength. Your error rates go up. If you're using a directional antenna, what you'll find is that sometimes you can actually intentionally bounce radio waves off of things. The same guy, Nathan, who was on that trip to Crater Lake, he was also up by Mount Hood. He does a lot of off-roading. And what he found was he could actually talk to our repeater in Eugene at 3,500 feet by aiming his antenna right at Mount Hood, which was north from where he was. So basically aiming it toward Mount Hood, bouncing the signals off and bouncing them south. That was the best path that he found, because Mount Hood is a big thing. It reflected the radio waves. Another one is called knife edge diffraction. This is basically pure physics. If anyone has been through high school or college physics, you might remember something called the single slit experiment. And the single slit experiment is where you basically aim a wave or a light beam at an open slit in a piece of metal or something, and you get waves that go like this, and you have an interference pattern that gets strongest in the middle, but it's not zero everywhere else. You end up with interference and constructive and destructive interference. Well, that also means that some of the signal strength that you're aiming at that sharp object, for instance, will end up down here, which is nowhere near where you expected it to be. This is actually very similar to when you aim a signal at a mountaintop. Some of that signal diffracts over the edge, and you can actually talk to somebody on the other side of the mountain, even though you can't see them. And this is known as knife edge diffraction. Let's see. Okay, so one last thing before we take a break. VHF and UHF and HF radio. Okay, does anybody here have a microwave oven?
Yes.
Did anyone heat
Yeah.
up anything in a microwave this morning? Did you
Yeah.
know you used a radio transmitter
Yes.
Yep.
when you did that? Okay, does anyone know the operating frequency of a microwave oven?
No.
About 3 gigahertz to 300 gigahertz.
Nope. Microwave oven operates at 2.415 gigahertz.
Oh, okay.
And the question is why? Because anybody recognize this?
Mm-mm.
That's a water molecule.
That's water. Water has a resonant frequency of 2.5 gigahertz or 2.415 gigahertz. So when you put radio frequency energy into something that has water in it, its energy is transferred to the water molecule, which causes it to vibrate faster. Motion is another way to describe something called heat, which basically means when you excite water molecules at that frequency, they get hot. If you have something that has water in it, it gets hot. A microwave oven is a kilowatt. And how much is a kilowatt, everybody?
1,000 watts.
1,000 watts. A microwave oven is a kilowatt radio transmitter at 2.415 gigahertz. Now, curiously, 2.415 gigahertz is right next to what we call Wi-Fi. Has anyone ever noticed if they turn their microwave on, their Wi-Fi signal drops? Anyone? Anyone ever had that happen?
Hadn't noticed.
Well, that's why.
Makes sense now.
That's why, because they're right near each other. Your microwave oven, if it's got a kilowatt of energy being dissipated inside, if a little bit leaks out, this for your Wi-Fi is in the milliwatt range to make it work right. If you even get a couple of milliwatts of leakage out of your microwave oven, that will get into your Wi-Fi. So, given the fact that this frequency, which is in the UHF range, right? 2.415 gigahertz is clearly in the UHF range because the UHF range is 300 megs to 3,000 megs. This is called UHF, or 300 megs to 3 gigahertz, right? That's UHF. So this is clearly in the UHF range. What happens if I am legally transmitting a few hundred watts and my transmitter and antenna are launching a signal that is trying to get to another place? So I'm going to actually put a dish on this end, because I might put up a dish on this end. I might have a 20 element Yagi. And right in the middle of it, I have this thing called let's see if anyone knows what this thing's called.
A tree.
A tree.
Yes, a tree antenna.
Yes. Well, no, not a tree antenna, but what do trees contain a lot of?
Water.
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 And microwaves, what does microwave radiation at that frequency do to water?
Oh no.
It's live.
It excites it.
It excites it.
Vibrates it.
That's right. And in doing so, what does it do to all of its energy?
Makes heat.
Yeah. Well, how much
Absorbs it.
That's right. How much of your signal gets to the other
Yeah,
side?
it sheds the energy into the tree.
That's right. Basically, vegetation absorbs microwaves. Does anyone have like XM radio? Have you noticed that on a really rainy day you can lose your signal?
Or under trees, or under bridges, or next
under
to a
trees.
cliff,
Well,
or.
Next
Well,
to an
well,
18
well,
wheeler.
But bridges and bridges and hillsides, you can't do anything about those. But in particular, the effect of trees, a lot of vegetation, or a lot of rain can make you lose your signal. And that's why, because microwaves get absorbed by water.
So you use a copper nail, some coax cable, and turn that tree into your antenna.
You could. Actually, I want to say that I've actually heard of a tree being used as an antenna. It's not a great conductor, but it has electrolytes. Anything that has
I've also. Go ahead.
So one thing I've actually thought of that I wanted to try, if anyone's ever been to the ocean, that if you've ever seen like what happens to stuff that's left outside at the ocean, if it's metal, it corrodes because there's so much salt water. Salt water is a great conductor, and I've often said, I've often thought and known and said that you know, if the band is in really, if the 10-meter band is in really good condition, you could actually use a wet string as an antenna. I've actually thought that it would be interesting to soak a piece of string in salt water and keep it wet and actually try to use it as a low power antenna. I think it might actually work.
I have heard rumors of people putting string or a ground wire antenna into the ocean and being able to
Oh, that
transmit
works.
because of, yes.
Yes, that actually works. If you're near the ocean, you run the ground into the ocean, and that becomes your ground plane, and that's why that's why it works so well on sailboats. That's why you can do so well on sailboats, because you're using the entire ocean as your ground. Everybody ready for a 10-minute break?
Yes, please.
Okay.
Yes.
Yep, yep.
Okay.
Hey, Jim, any comments? I would pay you. It's not the date, it's the hour. Check the iron.
Hello, hello. Do we have any questions?
You don't?
Hello?
Oh, I guess since the floor is open,
Yeah,
um,
please.
yesterday I was curious if you've ever in your experience heard of anybody trying the original spark radio waves back from like 1912. I
There is,
saw just a
it's an
notion of it.
it's an illegal mode.
Oh, really?
Oh yeah.
So it can't be done anymore.
Mm-mm.
Man,
Well,
It's extremely non-selective.
yes, it makes tons of RFI all across. I mean, basically, you know how Spark works?
basically arcing electricity, but that's as much as I could gather from the
Okay,
article.
so between 2 points, you generate an arc. An arc is a pulse. A pulse of very, very narrow duration generates, if you do a Fourier transform, which is a frequency domain transform of it, what you end up with is, so this is your time domain, and we're going to cover frequency domain stuff. This is your frequency domain from 0 to infinity. Your signal basically looks like this. It makes the frequency components in a single lightning strike, for instance, are all, it covers all RF,
Right. Pretty erratic then.
right? So what you do then is you take this frequency thing and you run it through a narrow filter, which has a pass band, and it has a 3 dB bandwidth that looks like that. 3 dB is half power. Gee, I wonder where that came from, right? That's your 3 dB bandwidth. So this is your pass band of your filter. And so it is selective for whatever frequencies you want, but unfortunately it, kind of looks like this. That doesn't mean that it's zero everywhere else. So basically what it does is it creates noise everywhere. Spark is incredibly messy. And that's
Well,
why
thank you.
people don't do it anymore.
So my question, Scott, is about a part of what my interest here is using my 2-meter radio for paragliding and understanding all the pieces, that all the things that it can do, things like squelch and, I don't even know. I'm looking at the manual to try to make a list for you. Are we going to cover some of those kinds of issues?
Yep.
Awesome.
That's later today and early tomorrow, I think. How a controls of a radio.
Fantastic. This has been really entertaining and informative. Thank you very much.
And I hope helpful. So
When I was a kid, I couldn't talk on the phone, so my friend and we did the cans with the string across our yards.
isn't that amazing that it works? Yeah, it works.
It worked. I was really surprised.
Well, the one thing that you have to do in order, okay, and you can tell me why this works or doesn't work. You had to keep the string taut.
Right, and we did.
And why is that?
Vibration.
Right, because the slack string will absorb the vibration. If the string is slack, it'll attenuate the vibration. It'll just absorb it. So if you keep the string tight, it basically becomes like a solid element.
Doesn't that same thing go for power lines? That's why you hear the resonant hum through them.
I don't know that. I mean, it shouldn't, but I mean, the reason that you hear, like, for instance, in a power supply, if it's a big, if it's got big metal plates in it, the reason that you hear that is actually the fact that the plates are physically moving toward and away from each other as being moved by the magnetic field. Can't say, I don't know about power lines. I don't know enough to say. All right, antenna polarization. We are on to antenna polarization. Okay, so we have a couple of parts of an electromagnetic wave. I just gave you the title, electromagnetic. Again, we're going to draw this, and we're going to draw this, and we're going to draw this. There's the E field, and here's the H field. H is magnetic, and here's the S direction, which is the pointing vector, which is where it's going, and the energy is going. So here's our electric field, and here's our, if I can change colors, I hope I can change colors. Not letting me change colors. Magnetic field goes like this as the energy travels in the forward direction. Everything's perpendicular to everything else. The polarization of an antenna is defined by the direction of the electric field. The direction of the electric field is the direction of the electric field is parallel to the wire. So if I have a piece of wire that looks like this, my electrons are moving back and forth. These are parallel to the ground. That's horizontal. This is known as horizontally polarized. If I have an antenna that is vertical, my antenna is going up and down. My electrons are moving up and down. This is known as vertically polarized. That's it. That's polarization. Polarization is the direction of the electric field. The electric field is defined by the orientation of the wire. So if I have a car, for instance, then my car looks like this. I'm really bad at drawing cars. It's tiny, tiny wheels. Here's my antenna. What would my antenna on the car be? Horizontal or vertical?
Vertical.
Vertical. And in fact, this is very often the most simple antenna, which is a quarter wave vertical antenna. Now, if I were to do this on my house, I could do it on my house. The trick here is that we're now going to draw a very simple antenna. And again, this is the quarter wave antenna. The
ground plane, correct?
Yes. Now, in order to understand how an antenna works, you have to look at the direction of motion of the electrons in the antenna. In this case, they move up and down. If I were to draw a horizontal antenna that looks like this, they go side to side. As they do this, they generate electric and magnetic fields. And what we are interested in is the direction of maximum radiation from an antenna. So this right here is the most basic antenna. And I know we're not on this yet, but it's important that I draw it. This is a quarter wave long. This is a quarter wave long. The total length is a half wave, and this is known as a dipole. A dipole is a fundamental antenna. It is the most basic antenna there is, and it's the basis for most antennas that exist. The reason being that if I draw this as a half wave long, physics tells me something about the endpoints. So let me ask a question. What is the current? Remembering what current is. What is current again, everyone?
Flow of electrons.
Flow of electrons. What is the current at the end of a wire?
Non-existent.
That's right, it's zero. So if I were to draw a current distribution, and I know that I have an antenna that is a quarter wave long on each side, I can draw a current distribution that is in the shape of my wave. And what does it have to be on both ends?
The same.
Zero.
It has to be zero. Yeah, it has to be zero. So basically, this antenna, which is a center fed half wave dipole, it basically allows this center point to go to its peak value because it allows me to draw an entire wave or entire half wave, and it meets the boundary conditions that say that the current has to be 0 at the end. Now, what if I were to take this antenna and I were to make it a little bit longer than a half wave? And I start drawing my wave. What does the current at the end have to be?
Zero.
0. And I start drawing it like this. And I have to do the same from the other side. Where does it peak? It peaks somewhere away from the center, right? Well, that might not be too bad, but I still get some current peaks. Maximum current is what launches my most energy. So that's actually not too bad. Now, if I change this again and make it too short, and what's my boundary condition that I still have to meet? What's my current at the end?
0.
0.
Zero.
Do you see a problem here? Where's the rest of my wave? It should be a lot higher than this, right? Those peaks should be a lot higher, but the constraints of the antenna, the fact that I've shortened it, means that I never get to that point. This is not a very efficient antenna because it's too short. It never gets to peak current because physics says that it can't. So that is why we always try to make an antenna that is a half wavelength long or potentially longer, but we start at a half wave. Now, the other thing about a half wave dipole is that I have to feed power into it. This is called feed line. Right here, feed line is something that transfers power from my transmitter to the antenna. It gets me up to peak current right in the middle. If I were to look at this point right here, I would find that my feed point impedance, remember impedance is the letter Z, is equal to R plus IX. That's that whole two-dimensional plane thing where this is the resistance and this is the reactance. I want no reactance. I want it purely resistive so I can use up my power as launching waves instead of heating things and doing all other kinds of weird stuff. This has an impedance of about 72 ohms. Well, my transmitter has an impedance of about 50 ohms. My cable, typically when I buy it, has a characteristic impedance of about 50 ohms. This is actually a pretty good match. It's pretty close. I can actually very easily make do with this antenna. And what is the formula for, what is Ohm's law again, everyone? Ohm's law, basic Ohm's law? E equals what?
I over R.
Nope. Got to memorize that one. E equals I times R. Okay. Now, in this case, we are replacing R with Z. So it's actually E equals I times Z, where Z is our impedance. So if we have a Z of 72 ohms, we know that we somehow got it by taking E and dividing it by I. Well, we know that our current is what? Right there in the middle. Is it big or small?
Big.
It's big, yeah. Okay. So we know that our voltage must be such that our E is not terribly high because our current, our current is not terribly high. But now let's move this. So what we're going to do is we're going to take this antenna and we're going to shift it a little bit. And I'm going to take the feed line and I'm going to move it. I'm going to put it over here so it's off center. So now, what do you see about my antenna? Is it still a half wave antenna?
It is not.
It is. It's still a half wave long. I haven't changed the
Oh.
length.
Oh,
All I did was I changed where the feed line is connected. But what happened to the current at that point?
Diminished.
It went down. That's right. And since Z equals E over I, my current went down. And in fact, my voltage went up a little bit because the voltage at the end of the antenna actually gets higher and higher. So what happened to my impedance? If the numerator got bigger and the denominator got smaller, what happened to my impedance?
It goes up.
It goes up. So at the middle, it might be 72 ohms. Over here, it might be 200 ohms.
Oh,
How about if I feed it way at the end? I'm going to move it so that it's way at the end.
Drastically off.
Yeah. Okay. What's my current way at the end? Almost at the end.
Zero.
Almost zero.
close
Well,
zero.
yeah. Z is equal to E divided by I. What happens if my I is almost zero?
It's almost undefined.
Yeah, it's almost infinity. And in fact, if you feed it near the end, you have an impedance of about 5,000 ohms. Well, if your cable is looking for 50 ohms and this is 5,000 ohms, you have what's known as a problem. So then we actually start to need something called a transformer to change the impedance. Transformers can change voltages, but I'm going to show you that transformers can also work magic in another way. So everyone remember what a transformer looks like? That's a transformer. Two coils wrapped around a common core. Everyone kind of remember that from yesterday? We used it to change 120 volts AC to 12 volts AC for our power supply. This has a turns ratio, in this case, of 10 to 1. That generates a voltage change. Now, one thing that we know is that we have conservation of energy and conservation of power. What's the formula for power?
P equals E over
Nope,
I.
just pi. The word pi. P equals I
Oh.
times Z.
I times E.
I times Z. You guys need to practice this because these are absolute fundamentals of electronics, and you will use them over and over and over, even if you almost never even get on the air. This is important stuff to know. The P
First
equals
things to
I
write on
times-
your scratch piece of paper for the test.
That's right. So P equals I times E. Okay. So if I put, because this is a transformer, and let's say that I have a perfect transformer. It has 100% efficiency, and I put power in on this side. How much power do I get on the other side? They're equal.
Oh,
There's no power loss in an ideal transformer. Let's say that it works really well. I have no power loss, which means that E times I over here is equal to E times I over here. Or we'll write it in the more friendly format. P equals I times E, and P equals I times E. Okay, so we know if we have a 10 to 1 turns ratio that we have a 10 to 1 voltage ratio, but the powers are exactly the same. So P1 equals I1 E1, P2 is I2 E2, but the powers are equal, which means that IE equals IE. So that means that I1 E1 is equal to I2 E2 because the powers are exactly the same. And we can figure out that I2 over I1 is equal to E1 over E2. What does that mean? That means that our output current is 10 times higher. And we'll see that if this is 10 amps, this is 1 amp. That kind of makes sense. If you go through your power calculations, what's 1 times 120 on the left-hand side? 120. What's 12 times 10 on the right-hand side?
Same.
100.
Same thing. Okay, so we've conserved our power. Our power is identical on both sides. Okay, but now we have a bit of a situation, right? Which is, okay, we changed our power, we changed our current, and we changed our voltage. Well, okay, so let us say that we have a resistor over here that is 1 ohm. Well, or actually in this case, let's make this, let's make it work. So we're going to say that this is 12 amps so that it actually makes sense. E equals I times R. So on the left-hand side, we're going to have 1.2 amps. Okay, generated by a 1 ohm resistor. Okay, so now let's take a look at the left-hand side. We're going to do Ohm's law. E equals I times R. R equals E divided by I is equal to 120 divided by 1.2. What is that? 120 divided by 1.2, everybody.
100.
100 times. What's our turns ratio on our transformer?
10 to 1.
What's our impedance or resistance transformation? It's the
Times gain?
It's the square. If I had a 20 to 1 turns ratio on my transformer, I would get 400 times change on my impedance matching. Has anybody here ever seen a pair of headphones and the headphones say, for instance, 32 ohms impedance? I know somebody's seen this, or 8 ohms impedance.
Yep.
When you buy a pair of headphones, because they're coils, they'll say that.
Yes, I have seen it.
Okay, so
It's the wound copper inside the magnet.
That's
Or
exactly
around the
right.
magnet.
So, but now the question is, you have to look at what is driving it. It might be an output device that says high Z or 400 ohms impedance. Have you ever tried driving a pair of headphones, plugging in a pair of headphones, and it doesn't sound very loud, or it sounds like crap? The reason being that the impedance does not match. So what you end up having to do is, let's say you have a 400 ohm impedance driver. This is your stereo system, for instance. It might say designed for driving high impedance, and you have 8 ohm impedance headphones. What is the ratio of 400 to 8?
50 to 1.
50.
Gee.
Well, it's 50. And since a transformer can do impedance matching, and it's the square of the number of turns, and you need 50, where would you start? How many turns? What would your ratio be? Square root of 50, which is about
Throw
what?
over 7. Throw over 7 times.
About 7 times. This is impedance matching with a transformer. We use these for antennas. We use these for audio transformers. We use these for microphones. We use these all over the place. And that's impedance matching using a transformer.
So that's like when it comes to my competition stereo system, I run all my subwoofers are running at 1 ohm stable.
Yep.
So I'm running 8,000 watts to run everything at 1 ohm stable, and it runs perfectly clear and matched.
Mm-hmm. But the fact that they specify 1 ohm, they're giving you the impedance. So they're telling you if you hook them in series, you add them together. If you hook them in parallel, your impedance is lower, and maybe you need a transformer to change the impedance so that you don't blow out your amplifier. So this is all really important stuff. You don't necessarily have to know it for this, but there are so many real life aspects to what we're learning in this class that show up throughout electronics, throughout, this is everyday life. And most people don't even know that it's there. Okay, let's see. We're going to go back to this right here. Antenna polarization and phenomena. Okay, so now we're going to talk very quickly about interesting phenomena, a little bit back to the ionosphere stuff. Now that we've taken that little segue into antennas, the ionosphere, we have different frequency bands that use the E layer. The E layer is a weird layer. That long skip that we talked about really isn't useful for that much on the E layer. The E layer operates on 10, 6, and 2 meters. Sometimes we get something called sporadic E, which is, they think, caused maybe by thunderstorms, maybe by sprites. And that can be usable for a couple hundred miles to about 1,000 miles. Meteor scatter and auroral backscatter. Basically, anywhere that there's a large number of electrons, you can refract and bend radio waves around. You aim your signals at the aurora and it bounces back off and it sounds all weird and distorted. Meteor scatter. When a meteor burns up in the sky, that trail that you see is actually plasma. And plasma is basically a cloud of electrons and ions. You aim your antenna at a meteor trail and you bounce signals off of it. That's known as meteor scatter. 6-meter band is where we typically do that. We also have something called ducting. Tropoducting, or using the troposphere, which is the area that we live in. If anyone has ever been driving down the road and seen what looks like a mirage in front of them, which looks like water, blue sky, that's actually a very, very very, very small version of tropoducting. And it's caused by temperature inversion right over the highway. And that causes a change in the index of refraction of the air. And you basically get the air, the sky refracted up into your eyes from the surface right above the roadway. Again, microwave frequencies. Microwaves are absorbed by precipitation. But if you get away from the microwave bands, such as the 10-meter band and the 6-meter band, 10 meters at the upper end of the high frequency band, 6 meters is at the low end of the VHF band, rain doesn't have any impact. Okay, the ionosphere bends and refracts waves. You can get long distance communications. I think we covered that ad nauseum. During this peak of the sunspot cycle, and just so you know, everybody, we are almost at the peak. You are getting into this at possibly the best time, because it's an 11-year cycle where we go through a very, very big valley and then a really nice peak where we get a lot of ionizing radiation out of the sun. More ionizing radiation means higher levels of electron clouds and ions, which means we get more stuff up there. The more stuff there is, the higher the frequency we can bounce around, which is why I said when the 10-meter band is open, you might be able to use even a wet string. When the 10-meter band is good, 10 meters is great. When the 6-meter band is good, the 6-meter band is great. We went for about 6 years where there was nothing on either of those bands at all. That was in between sunspot peaks. And it's a very sad time. The best time for 10-meter propagation, as we saw on the map, is from dawn to shortly after sunset, because 10 meters requires a lot of ionization. Irregular fading of signals. Okay, so if you happen to be carrying a handheld radio, you can move a foot to one side. But what happens if you're on the 20-meter band and You think, oh, I'm just going to move a half a wavelength. How big is a half a wave at 20 meters?
10 meters.
10 meters, that's 35 feet. And your antenna is probably either on a pole or on a tower or hanging between two trees out in your yard, or tied to a mast that's anchored to a fence post or something. You're not going to move it. So what you end up with is the fact that, let's say I'm talking, the signals start to come back, and now you can hear me again, and then they start to come back. That we know that is known as, in the ham world, QSB, or fade. And fade is caused by combining of signals that take different path lengths. The ionosphere that we talk about, where all those electron clouds are, is not, and I use the word static, it is not a static thing. It's continually moving. The ion clouds move up and down and side to side and change in thickness and change in density continuously. A path between 2 points might be fine and then all of a sudden disappear. But then 10 seconds later, it comes back, and then it goes away again, and then it never comes back. So that's basically what ends up as a result of all of those things changing 600 miles up. On the high frequency bands, polarization of your antenna is not particularly important, because by the time the signals go up there and get all twisted around by being bent off of those ions, those clouds of ions, it's typically elliptically polarized. With elliptically polarized means that there's some vertical and some horizontal. So it doesn't mean you don't have to maintain the polarization that you have. So right now, what we're going to cover is that polarization thing. So does everybody remember what we talked about when we said, if we have an antenna that's parallel to the ground, what is the polarization? Horizontal or vertical?
Horizontal.
Horizontal. If we have a vertical antenna, is the polarization horizontal or vertical?
Vertical.
Okay. So let's say we have a vertical antenna, and here's the electric field going up and down. And then we have a horizontal antenna, which I'm going to redraw. I'm going to try to use my isometric view like this. And this would normally be receiving signals that have a polarization that look like that. Are these antennas going to be able to talk to each other very well?
No.
No, because the electric field that is generated causes excitation in the other antenna. If it is not looking for the right polarization, it's not.
Would they be out of phase?
No, they're cross polarized to each other.
In
other words, the movement of one. So the easiest way to think of this, has anyone ever used polarized sunglasses?
Yeah.
Okay, why do polarized sunglasses work? So here's your polarized lens. Your polarized lens has a bunch of vertical slits in it. So do you think because those are open spaces, do you think that horizontally moving light, which goes left to right, when it hits those vertical open slits, what's going to happen to it?
It cancels out.
It cancels out. They don't pass through. How about the light that's moving in the vertical direction? Electric field in the vertical direction.
It gets through.
Yep. So this is basically what happens when the sunlight hits your car hood or the roadway. Because of the shape of the road, it actually selectively picks the glare. The glare becomes horizontally polarized. So if your polarized sunglasses only allow vertical through, they cut out the glare. Similarly, if I have an antenna that looks like this, straight up and down, and I have waves that are basically carrying energy in this direction, it takes energy going up and down to make a signal in my piece of wire. How much signal is going up and down if everything's going side to side?
Very little.
Yeah, this basically disappears. Your signal, your attenuation by doing this, by having the wrong polarization, could be like 30 decibels. And what's 30 decibels? That would be loss. That's 0.001 of the other signal strength. 1/1000th of the other signal strength that you would normally be getting. So polarization is extremely important, matching the polarization of the antennas, at least in line of sight. So now what we're going to do is say, okay, let's draw this dipole antenna. This is parallel to the ground. If I am, let's say, looking at a dipole from the end, right? I'm going to draw a dipole from the end. Looks like a dot, right? If I'm looking at the end of a piece of wire, which way is this going?
Your mic just cut out for me, Scott.
There we go. Sorry. I need to move that further away from me. Okay, so that piece of wire, does it matter? Does it care whether signal's going up or down or side to side?
Nope.
Nope, it doesn't care. It doesn't know the difference. Now, by putting this over a ground, maybe you get a little bit of ground reflection going this way. But how about the signal going up into the air? Directly up. What does that do for you? Not a lot.
Unless you're talking to a satellite.
Yeah, we call right. Well, yeah, we call that a cloud warmer. So so we have most of the interesting stuff is parallel to the horizon. But these are all equal energy. Now, so you basically have symmetry in that direction. So now what I'm going to do is draw this again from the front. And here's our wire. So we have stuff going that way and that way and that way and that way and up, like in the shape of a donut. How about along the wire? It turns out we actually don't have virtually any radiation along the wire. So this actually forms the shape of a donut or a figure 8. So a dipole has a radiation pattern going into space that basically looks like a donut around the wire. So now what we're going to do is say, again, what use is this? Well, we're going to try to make use of the stuff that goes along the horizon, because that is the stuff that goes long distances or a little bit above. So those are that's what's of interest. So now let's change this up a little bit. Let's instead take this antenna. We're going to have the ground and we're going to make a dipole and we're going to do this with it. We're going to make it vertical. So which direction does energy get launched out of this? Perpendicular to the wire.
All directions horizontal.
All directions in the horizontal plane. And does it care which direction in the horizontal plane is more important than any other? No.
Not a bit.
Not a bit. So a vertical antenna is what's known as omnidirectional in the horizontal plane. If we look at it from above, a vertical antenna is a dot. There's no symmetry. There's no issues with symmetry. It transmits in every direction. So, which is a better antenna, do you think, for low angle radiation?
Vertical orientation.
Yeah, vertical. And in fact, that's why if you can't put up like a directional antenna like a Yagi, a vertical is a very good choice. Now, it also turns out that a lot of noise that's generated in the world, for whatever reason, is easily picked up by vertical antennas. So they tend to be a little noisy on receive, but their radiation pattern is very, very good for the horizontal plane for sending off signals low to the horizon. Now, another problem with this though is that what do you notice down here at the end? At the bottom. What's it really close to?
The Earth.
The Earth.
Ground.
Okay. Now, if I draw our current looks like this. We have no current at the bottom, but it's also important to note that where we have low current, we typically have high voltages. So the red dot would be the voltage curve. So if we have a high voltage right here, and it's sitting right above the ground, what does that mean? Anyone ever?
Potentially hazardous.
Anyone? Yeah, capacitor. So yeah, capacitor arcing. So typically, if you're going to do a half wave dipole,
RF
vertically,
burn.
RF burns, yeah. But we're really looking at power loss. You know, some of your power goes across. This forms a capacitor, and that high voltage leaks power into the ground. So basically, that warms up the ground, which doesn't do you a whole lot of good. So you either want this a lot higher than the ground, or you're just going to say, to heck with it, we're going to build something totally different. So a dipole is the fundamental antenna. Here's the second fundamental antenna. That's it. That's the other fundamental antenna. It's a vertical, right? It's vertical. It's a quarter wave long. We call this a quarter wave vertical. And in particular, because of this thing below it, which is the ground, we call it a quarter wave ground plane vertical. If we draw our current distribution, still has to be 0 at the top. It comes down. It's maximum at the bottom. Our voltage is still high at the top. So where's the other half of the antenna?
The Earth.
Yeah, actually, this is a
Here.
trick. This is a trick. That's right. So what actually happens here is that the other half of the antenna is down here. So if you were, let's say, looking at this from over here using a telescope, right? And you didn't know that this was a reflective surface like a mirror or the ocean, and you looked over here, how many pieces of an antenna, what would you see? If you were looking at that, what would you actually see if you didn't know there was a mirror there? How long would that antenna be?
The half wave.
It would be a half wave, because you cannot tell that the top part of the antenna is being reflected and tricking you into realizing that there's another part of the antenna there, which really isn't there. So a ground plane vertical works fine so long as you have a ground plane. So this basically means that you need that ground to be a really good ground plane. So if you happen to live near the ocean, salt water is a great ground plane. If you don't have an ocean nearby, what you would typically do is you would dig up your yard, which is why a lot of people don't want to do this, and lay down something. If this is a really big antenna, lay down an array of between 16 and 120 ground radials that go in the ground. That becomes the bottom half of your antenna. For those of us who don't have the space to do that, we obviously don't do that. But don't worry, there's another version of this that we use for other applications. And it looks like this. This is a quarter wave long. And this is only 19 inches long.
It's like using a pie plate or a pizza pan or something.
I've done both of those. And if it's 19 inches long, this is a quarter wave radiator for the 146 megahertz band, which we know by going 300 and 146 That's about 2 meters. This is a 2-meter band. This is a perfect 2-meter quarter wave vertical antenna. And what's interesting about this is that you can build this. Like I have one of these up on my roof. 1, 2, 3, 4. This antenna has a feed point impedance of 36 ohms. If I take it and instead come up here and I bend the radials downward slightly, I can get an impedance of 50 ohms. Most coaxial cable is 50 ohms. That is a perfect antenna match for that cable and a perfect antenna match for my radio. Its gain is quite low, but I don't really care because it only cost me $5 to make. And it works really well for $5. Now,
Are you using that mostly on HF?
how long is it?
No, the question I had was with the radial, prongs or whatever. Is that I heard a reference where it's mainly used with HF.
All right, let's look at the geometry of it. So we're going to make a, let's say, a 20-meter quarter wave. Okay, so this is a quarter wave. What's the approximate length? To find the length, you take the frequency. So let's say we're going to cut it for 14.100. So we're actually designing an antenna now. 14.100 megahertz. We use our formula, 300 F lambda. We have our frequency of 14.100. Get my calculator. 300 divided by 14.1. I get 21.27 meters. Okay, and how long does it have to be? Quarter wave, so divide it by 4. I get 5.3. 5.32 meters. Okay, now to account for, this is something that's really important, to account for the real world self-inductance, insulation, things like that, we're going to shorten every antenna that we make by 5%. That's called we call that a fudge factor. So 95% is 5.05 meters. And just to turn it into feet, we're going to multiply that by 3.3, and we get this being 16.7 feet. Okay, so how long are my radials? They're going to be about the same length. So if you have a practical way to put up radials that are in the air, because if we're doing something that's a true ground plane vertical, where the radials are sticking out from the thing, they have to be stretched out, and they're going to be about 17 feet long. I have built one of these. I actually use ropes on these, and I put this on a big pole. It works really well, but it's one of those things that you're going to have space for it. You're going to have anchor points. Does that answer the question?
Yes, thank you.
Okay.
Okay, crazy question.
No such thing.
Could you build a saltwater pool in your backyard and use that as a grounding for your antenna?
I mean, yes, but the question is it going to be big enough? Depends on the frequency. It depends on the frequency you're talking about.
Okay.
I'm not sure I understand something I think is a little fundamental, Scott, and let me know if it's taking us too far back, but it seems to me you're talking about the wavelength of an antenna, and yet my radio works on many wavelengths, my car radio and etc.
That's a problem, isn't it?
It seems like it.
That's a problem. Well, there you go. That's a problem.
Yeah, I bet you got a solution. I bet you can explain it, but
well,
I'm not thinking through it.
Well, no, you exactly got it. So, what are you thinking is the fix?
Multiple taps.
You can have multiple antennas. I mean, which radio are you talking about? The car stereo, or are you talking about a mobile radio, or?
Well, each of them has a wavelength range that they receive. And so I'm not understanding why, if we have a fixed quarter wavelength
That's a problem, isn't it? Are you talking, so you're talking FM radio
Well,
or
sure.
AM
let's
radio,
talk-
right? We'll just
or my
start with that.
or my handheld 2 meter.
Yeah. Okay. Well, FM radio is 88 to 108 megahertz. Now, how about AM radio? 530 to 1700 kilohertz, which is 0.53 to 1.7 megahertz. Those are really different, aren't they? This has a wavelength of about 3 meters. This has a wavelength of about 300 meters. Okay, tell me what the problem is.
Well, I mean, my best guess is that you adjust the impedance somehow, but
You
that's
could. I mean, but I mean, these are 2 orders of magnitude different. So the way that they achieve this is that the FM radio is a quarter wave sitting on the front fender of your car. And the nice thing is that it's a vertical antenna, so it doesn't matter which direction it's receiving from. It doesn't matter if you turn left or turn right or right. It's always vertical. And FM radio antennas, the transmitters are all vertical, so they're omnidirectional. So you have your coverage area. Everybody can hear, depending on which way they're turning. How about AM radio? How do you stuff a 300-meter antenna, or in this case, we'd cut it by a factor of 4. So let's say it's only 75 meters long. That's 250 feet in length. To my knowledge, nobody's dragging 250 feet of wire behind their car.
Use the body of the car.
You could.
If you bonded it.
Yep. What they typically do, though, is they do this.
Coils.
And
Inductive loading.
And they wrap that around a ferrite bar. If you were to rip open your car radio, you would find that inside the car radio is that. That is your AM antenna. Essentially, it is incredibly inefficient, and it's inside a metal box. But it's good enough.
Right.
So yes, that solves the problem of having 2 completely different frequencies and completely different wavelengths.
Prime example would be my Camaro. With the stock antenna, I get crap reception. As soon as I go to AutoZone and I buy that antenna that they sell and plug it in, all of a sudden AM, FM, everything comes in crystal clear. It's because you're taking that antenna outside of a metal casing. Same goes for any of our ham antennas.
Yep.
If you're building a wire antenna, you don't want to stick that inside of a metal sleeve. You don't want to go to Home Depot and buy wire that's in a conduit and try to use that.
Right.
You want to use a thin-walled PVC to protect your wire from the rust.
Yep.
So that you don't ever have to replace it. It's
Well,
the same thing, pulling it out of the metal box.
Here's the other thing. Let's say that you're inside a car, right? You're driving along in your car. Notice no back seat. And you have a radio. Here's your steering wheel. And your other hand is holding a radio up and you're using it, which you shouldn't probably be doing in the car anyway, but you're inside the car versus you have a piece of wire that goes up to an antenna on the roof. Which one works better?
Roof.
By a factor of 10, by a factor of 100, because the radio inside the car has to deal with the fact that it has all this metal that is blocking the signal from getting outside. Whereas if you put the antenna on the roof, it's actually, and you can slam a cable in the door. It's okay. That's what I've done for 30 years. You just stick an antenna on the roof and it actually uses the body of the car to enhance your signal. Now, the other question is, okay, well, let's say that I have something called a mag mount, which a lot of you will probably end up with. A mag mount looks like this. Here's your cable coming in on the left. Here's your antenna sticking up. There's a little connector down here. And down here, there is a plate, and the bottom part is connected to there, and the top part is connected to there. So how is it that even though it's a magnet, which has a piece of plastic at the bottom, which is electrically insulating it from the body of the car, why does this work?
Ground plane.
Yeah, but what about the ground plane? What's
It's like
making it work?
It's like a capacitor.
This is a capacitor. Notice it's two plates. That allows the body of the car, because this is AC, to be connected, coupled to that plate through that empty space. Isn't that cool?
Well,
cool.
that also goes for like a lot of us in the hobby. We've got the mounts that are the side clips for either our hood or our trunk lids, whatnot, right?
That's different.
Same thing there.
That's different. If you do that, you actually have
Okay.
to, what you actually do is when you clip it, you end up scraping the paint. And when it digs in
ground
and it goes through the paint, that actually physically grounds it.
Okay, follow up on the wire antenna being wrapped. The way you've drawn each of these is a long wire, and the wavelength, I imagine, going through space has a length.
Yep.
Why does it work if you coil the wire and stuff it into a small space?
We're getting to that in just a second.
Cool, thank you very much.
Great that you would ask that. Okay, here we go. Okay, let's see, let's see. I love it when people go a little bit ahead. I actually really do. I love a good discussion. Matt, you're dropping out. Okay, the frequency of a dipole antenna. When you shorten an antenna, what happens to the frequency? It goes up. When you lengthen an antenna, the frequency goes down. And antenna loading. Okay, this is the question that you were just asking. Okay, now I could take a piece of wire, and let's say that I make an antenna for the 6-meter band, and it's a quarter wave long. So we're actually going to go through and do the calculation for this. We're going to cut it for 52 megahertz. Okay, so 300 divided by 52 is, given the calculator, 5.77 meters. Okay, we're going to make it a quarter wave long. Divide by 4, 1.44 meters. Going to shorten by 5%. Going to take 95% of it. 1.37 meters times 39 inches per meter is about 54 inches. Okay, so we now have a 54-inch long vertical antenna. Electrically, if I have it over a ground plane, that's a perfect antenna. It's 54 inches long. It'll work great. Now, let's say I don't have room for 54 inches of antenna. And instead, I do this, and I take my 54 inches of wire, I add a capacitor into this so that I cancel out some of the inductance, which I'm not going to show right now. But it turns out that I can coil it up so that my whole antenna is only this big. And it's 16 inches long physically. But I used 54 inches of wire to make that coil. This is known as loading. And when you do this, you physically shorten an antenna, but electrically it is the proper length. And that is done for, spacing requirements. And typically you're going to do a little bit of, a little capacitor here or something like that to balance it out. So now the question is, what do you lose when you do this? Now, Steve, what do you lose when you do that? Did we lose Steve? There he is.
I'm going to guess current.
Current's still there. I mean, you can't change physics.
At peak power.
So what's going to happen? No, the power's still there.
You lose efficiency.
You lose efficiency because if I have this antenna and the current curve, current is what generates it. Every little chunk of current generates a launched wave. If instead I take this and do this with it, some of the current is going that way, at the time, some of the wave is going that way and this way and this way. And what's going to happen to some of those waves?
Cancel each other out.
They're going to cancel each other out. So what happens is my efficiency goes way down. So I might have, if I consider this a reference of 0 dB, this stubby little antenna might have a gain of minus 10 dB, which means if I were to put, let's say 100 watts into this antenna, how much power would I get out of this one?
10.
10 watts. In other words, I put in 100 watts and I only get 10 watts out. That antenna is going to get really warm too, isn't it? Yeah. That's why we typically don't do that, at least, for high power. But let's say that this is where system design is really important to understand. Let's say that I have a repeater station and I'm living or working right next to the repeater antenna. And here's me, and I have a handheld radio with a teeny tiny antenna, or maybe even virtually no antenna. But not only am I line of sight, I'm only 100 feet from the repeater. And I have an antenna that has a gain of negative 30 dB, which is 1/1000th of the incident power coming in that actually makes it into my radio. There's a good chance I'm still okay. Why? Because this has so much excess power and gain because I'm so close to it that I can actually absorb that minus 30 dB and I'm still okay. But if I take that same thing and instead of being right close to the whole system, like here's the repeater, and here is a bunch of hills, and here's me, I want to use as much gain as I can possibly get. So that stubby antenna isn't going to work very well. And that's where efficiency comes into play. And that's why I might want to get an antenna and put something, put it up in a tree or get a temporary tower or something like that. So at least I have a chance of making that contact. I've essentially decreased the amount of loss that I get between the 2 points by trying to tilt the odds in my favor. Okay, so let's see. What is a beam antenna? A beam antenna is an antenna that concentrates signals in one direction. Antenna gain. Gain again is how much signal you get in one direction compared to another. A Yagi is a specific type of a gain antenna. And now notice we actually just covered short flexible antenna supplied with a handheld radio. This is also known as a rubber ducky. Sometimes we refer to it as a dummy load. A dummy load is something that just burns up power without putting out a signal. It's not very efficient. A 5/8 wavelength antenna is better than a quarter wave antenna because it has a lower angle of radiation and more gain. So when I say radiation patterns and angles and things like that, what we're going to do is we're going to draw the dipole. This is a dipole. We're going to draw a vertical, we're going to draw a horizontal dipole. This puts out energy in that direction and that direction, and also up and down. But now what we're going to do is we're going to say that this has a reference amount of power, and this is we're going to call 0 dB. That's our reference. So it has no gain compared to itself. And now we're going to add another element called a reflector.
Okay.
Reflector is a spaced parasitic element. This in the middle is just a dipole. So we're going to feed it like a dipole. But now we've added this parasitic element, which is a little bit longer and spaced about a quarter wavelength behind it, and a little bit longer. And this energy that was going backwards is absorbed and re-radiated in the forward direction. By doing this, we can get a few decibels of gain in this direction. We've canceled some of the signal going backward and we've increased the signal going forward. We can add another element, which is spaced about a quarter wavelength from it. And this one is shorter, and this is called a director.
A Yagi.
It is becoming a Yagi. So now we have a 3-element antenna. This is the director is a little shorter, and it actually makes a more favorable path and tends to absorb energy and re-radiate it in the forward direction. So by going from 1 element to 2 elements to 3 elements, we've actually taken more of our power from the backward direction and sent it forward. So at this point, we may have a gain of 7 decibels. As you add more directors, you can get up to 9 or 11 or 12 or 20 decibels. So basically, by adding parasitic elements, you can direct more of your energy in one direction. That amount is called gain, antenna gain. Now, the other thing is that you have some signal that's still sent to the back. So you have the forward direction and the backwards direction. There's actually a ratio known as the front to back ratio. And this is a measure of how much power is going forward versus how much is going back. So you have front to back ratio, and you have gain. When you build a Yagi antenna or any directional antenna, these are your goals. When you put up a directional antenna, those are your goals. If you were to build, let's say, a dish that looked like this, and it is multiple waves in length, here's your horn, there's your transmitter. This is a parabolic antenna. This is a beam because it sends signals out in one direction. If this is a big enough antenna, you might have a gain of 30 decibels at a given frequency. That means that compared to a reference antenna, which would be a dipole, your forward direction energy is 30 decibels stronger, or 1,000 times what a dipole would do. That's why it's important to understand how decibels work. So if I put in, for instance, a power of 10 watts, how much effective energy am I getting going forward? 10,000 watts in the forward direction. So that is equivalent to running 10,000 watts with a dipole antenna. And that is why you are taking this class, because it is important to understand that, because 10,000 watts at the right frequency pointed right at somebody can do a lot of damage. Everyone ready for a 10-minute break?
Yeah.
Yep.
Okay.
Yeah.
Think of more questions.
Very good.
Hey, I'm back if anyone has any questions.
You just gave me a good laugh when you were mentioning mag mount and, you know, clamp mount and all that, because I've got both on my vehicle.
Mm-hmm. Well, you know,
Which I think I'm going to go switch over today. I think I'm going to go get me another. I think it's an SD by 4 or something like that antenna. It's a 4-foot whip.
Okay. Well, you know, it's really kind of funny because my first new car, which was not quite new, but it was basically new. I said, you know, I'm going to do this right, and I got I got a 3/4 inch green leaf punch. I put a hole in the roof of my brand new car and put on a Larson vertical on the roof.
Nice.
And you know what though? I mean, there's something that happens to you when you punch a hole in a piece of metal on a car and it's no longer waterproof. You're like, oh my God, what did I just do? You know?
Yeah.
You know,
That's
well,
funny.
but you know what's really funny? When I got rid of the car 15 years later, it finally died. I unscrewed unscrew the antenna from the roof. I had never taken it off, and I used CRC 400. If you're familiar,
Oh,
with
yeah.
that? Yeah.
Oh, yeah.
Yeah. It's a corrosion preventative, and it's this nasty, really, really good stuff. That was that underneath underneath the mount was the prettiest part of the car paint wise.
It still probably looks brand freaking new.
It looked new. The paint was shiny and it was reflective, and everything else had gotten dull and chipped. When I took that off, that was the prettiest part of the car.
Yeah, the boys at HRO wanted me to pop a hole in the roof of my Volkswagen. I'm like, yeah, no.
Yeah.
I will clip mount this all day long. I'm never popping a hole in this car.
Well, on that car, you know, the other thing is that if you're going to be doing HF, if you're going to be doing mobile HF, it's really important to make sure that that the whole car is a proper ground plane, and you can't trust the welds that the manufacturer does to be RF, basically RF welds, RF solid. So I took the hood of the car and I basically ground off some paint, and I ground off some paint on the mount on one of the engine mounts, or one of the strut towers, and I used big fat copper strap, and I tied those together, and then SP 400 did the whole thing. I did the same thing on the trunk. I did the same thing on some of the doors, and I did the same thing on the exhaust system.
Nice.
So basically everything from the roof to the hood to the trunk to the exhaust pipe was all grounded together.
Yeah, I'm a stereo head, so I have everything already grounded, and I run 2 copper ground straps under the car to drag.
Yep.
Just simply and I have everything grounded together, so anything and everything is just beautiful and clean. But
and speaking of that, speaking of loading, the antenna that I used was known as a screwdriver. If you've ever heard of one, it's basically it's an 8-foot whip on top of a variable coil that's driven up and down by a cordless screwdriver motor.
Yep.
And you know what? One of the best antenna systems I've ever had.
I'm not surprised.
Even on like 40 meters where it's electrically short.
Yeah.
It was so good because the coaxial cable, which we're going to get to, the cable was only 10 feet long. There was virtually no loss in the cable.
Yeah, I'm running 8-foot cables on my antennas.
Yeah.
The SDRs that I run come through the headliner and into the top of the handhelds.
Mm-hmm.
And people look at me like I'm crazy for running that antenna on
Oh.
handhelds, but guess what? It's the best damn antenna there is.
I forgot to mention that too. My brand new car, after putting the hole in the roof, I of course had to drop the headliner. I took out all the seats and all the carpet. Brand new car.
Oh, they probably thought you were weird by the time you came back.
You know what? Like I said, it worked great. It lasted for 15 years. And I actually I actually took the radios and I bungeed them underneath the seats.
That's what I'm going to do with the 500 once I can go pick it up.
And
so I think, Scott, I think I in your answer to the question about the length of the antenna, am I following correctly that you're saying, you know, you have to have one antenna length for a range of FM, right? So it works pretty well.
Yes.
At a quarter of 3 meters.
Right. You'll basically. So what'll end up happening? We're going to get into standing wave ratio and matching and things like that. But when you start to get away from the I mean, really, when you think about it, when you build an antenna and you cut it to length, it is cut and resonant for one frequency, ideally.
That's what I'm hearing you say. Yeah,
but if you're not, but let's say, but if you're not transmitting power into it, right? You're just using it as a receiving antenna. Does it really matter if 20% of the signal that comes in is gone? Does it really?
No, it doesn't.
It doesn't really. Now, because you're not generating heat with it or anything like that, it's just the signal that's coming out of the atmosphere. So, you know, that's why it really doesn't matter for that receiving antenna. They get close. And so, you know, maybe it's a perfect match at 100 megahertz and it starts to fall off a couple megahertz away. And by the time you're at 88 or 108, so the SWR is 2.5 to 1 or something. Because that's a very wide range. I mean, from 88 to 108 is 20 megahertz, and you're at 100 megahertz. That's 20% of the frequency that you're at. That's a very wide antenna.
I mean, this is the 2 meter from Yaesu, and it obviously I use it to transmit as well when I'm, you know, saying, hey, I landed
okay,
safely.
But you're using that from 144 to 148,
right?
And it's that's a 4 megahertz spread compared to a center frequency of 146. Right. So 4 out of 146 is only about 2.5% of the total band of the total frequency you're on.
So I'm not.
I have caught myself playing around and literally building antennas for each individual frequency, and I'll probably end up with 12 radios just because why not keep a radio on each individual frequency? You know what I mean? Or put in a switch and switch over. I haven't decided yet.
But that's why you can get away with like using that single handheld antenna for the entire 144 to 148 band. Now, if you were to say, okay, I want a single antenna, I want that, and I'm going to be transmitting from, you know, that same 20% of the band, which at 150 megahertz would be 30 megahertz bandwidth. Yeah, good luck. You know, then you're talking something more specialized at that point. But that's how they get away with it.
We get up to sort of 154 often, but
on what?
On this.
Do you actually use it for that?
Yeah, sometimes.
For transmit?
Yeah, I mean, I'm trying to talk to other people while I'm flying, and we'll pick a 158 or something like that. We'll pick a frequency and use that. Well, we're pretty local, right? I mean, we might be within a few miles of each other and in the air with no ground in the way, no mountains in the way usually.
Well, I mean, but when you say 158, what band are you on? Or am I just gonna say la 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 la? I don't hear anything. I mean, what band are you on?
I'm not sure what you're asking.
Like, are you using that now?
I think he's on 2 meter.
Are you, because if,
2 meter.
if you're talking on 2 meter, then it's only 144 to 148.
Well, I mean, all I know is the number on the radio goes up higher than that.
Well,
So,
for on receive, yeah. Unless it's been specifically opened, but let's take a look at that frequency chart, because that's, you know, this is the limit. Hold on, band plan update. Let's look at the 2 meter band. It goes from 144 to 148, and that's it. So some
He was
people,
actually on the airband there, Scott. So which is
Well,
different
yeah.
than
Well, so like if you're using the ham band, you're between 144 and 148. If you're using it for something other than that, I don't want to know. Like, you know, people will go out and buy a Baofeng, and I think right out of the box you could program that to work pretty much anywhere, right? That doesn't mean it's legal to do so.
maybe could
You
it
know?
be because we're FAA regulated or unregulated that as
Different-
paragliders we're allowed to
FCC, unless no, because it would have to be a type accepted radio to use somewhere else. I mean, if you're in some other band, I mean, like you can tune a handheld ham radio. You can probably clip a diode that's inside a handheld ham radio and open up wideband transmit. You know, there are some applications for that. You could tune it to 154.16, which is in the marine band, you know, marine FM, channel 16. That's the emergency call frequency on the marine band, but it doesn't mean you can use it.
Well, and that's what they used to do apparently is actually modify the radio to some degree, but it's a Yaesu FT65, and it came out of the box with this range up to I think 158. I don't know what the highest.
Well, on VHF it'll usually be like 136 to 174. And on UHF it could be as high as, you know, 500 megahertz on receive. And so one of the things we're going to cover is type acceptance and usability of equipment and what's required for a radio to be legal to be used anywhere. There are a lot of radios that are not type accepted. And one of the things about having a ham license is that you're expected to know all that. You know, like and that's why I said, you know what? La 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 la. If you're doing that, I don't want to know.
Yeah, okay.
So
I learned that this little radio right here the other day may or may not go into the 900s.
But, you know, we have a ham band there.
I know.
Between 902 and 928. So if it does, and it does so, and the spectrum is clean, then you could use it for that. So,
but I didn't know it did that, and I had it on my belt next to another radio, and it was transmitting. And I was like, man, why am I not hearing anything? And I realized that it was transmitting, and then I got a transmission back of open mic, please check your mics. I was like, that radio's listening to certain
apparently it can
frequencies that it shouldn't be able to transmit on.
If it's
like,
yeah, possibly.
That ain't good.
No. So, all right, let's see. Continuing on, here we go. If I'm still showing, no, I'm not. So let's go here. And that's the wrong thing.
Ooh.
Okay, we are into. There we go. Okay, feed line and connectors. Okay, feed line is what you use to get power from one device to another. It's connected. It allows you to connect a radio to an antenna, a radio to an antenna matching unit, which is known as an antenna tuner, or an antenna tuner, or a radio to an antenna itself. So this is where we bring together something called impedance. We've already talked about impedance. Impedance is something's ability to resist the flow of alternating current. Resistance is DC, impedance is AC. We use coaxial cable because it's really easy. It's fairly cheap. It's really easy to install. It's typically water resistant. You can bury it in a lot of cases. You can slam it in a car door and it's still okay for the most part. Most coaxial cable that we use is 75 ohms. Sometimes we'll use, or sometimes, sorry, 50 ohms. Sometimes we'll use 75, but most of it is 50. Now, notice I did say that a dipole antenna has an impedance of 75 ohms. That is one of the applications for that 75 ohm cable. The other reason that a lot of people use 75 ohm cable is because that is the impedance that's used by cable TV systems. And cable TV systems replace their cable all the time. So there are millions of spare feet of it laying around for very, very cheap. What happens as the frequency of a signal in cable is increased? Here we go. Okay, this is our attenuation chart. Everybody take a notice of what it's measured in. What are the units?
Decibels.
Per 100 feet. So as the frequency goes up, your attenuation gets worse. As your cable gets longer, your attenuation gets worse. So notice that starting at the top, that is, let's just pick 50 megahertz. RG174 has a loss of 6.6 dB per 100 feet. So every 3 dB is how many times? This is one of those two things you got to remember. 10 dB is 10 times. 3 dB is 2 times.
Yeah.
So if we have a loss of 6.6 dB, that's 3 dB, and 3 dB makes about 6, which is a half and a half, which means you only have 25% of your power coming out. Whereas the other 75% go? Keeps your cable from melts the ice on your cable. Exactly. Notice that as we go to RG58, this is very common cable. That's 4 dB, so that's a little better. Notice we go then to 8X. 8X is 2 dB. LMR, which is a manufacturer-specific land mobile radio cable, that's even better. RG8, even better. LMR 400. This is a high-end land mobile radio cable that a lot of people like to use. Notice at 50 megahertz, 0.9 decibels per 100 feet. In other words, almost no loss. But as the frequency goes up, even for LMR 400, it does get worse and worse and worse. But notice that it gets worse, but not as bad as some of the other cables. Okay, so as cables get longer, you get more attenuation. As frequency gets higher, you get more attenuation. Why do we use RG58 or 213? 213 is bigger cable. It has less loss because it's physically bigger. So now we can look at something called hardline. Now, what I would like to do is draw coaxial cable. This is coaxial cable. This is a section of coaxial cable. Here's our center conductor, where it disappears into the cable. And we have our shield, which is all around the outside. So we have two conductors. We have the center conductor and we have the shield. Okay, so we have in between these two things, we have something called a dielectric, which again is an insulator. So this is a dielectric. That can be air, that can be polyethylene, it can be polystyrene, it could be any number of different things that don't conduct. Most importantly, though, it just has to not conduct, but it's good that it fills up the space because then it maintains the spacing. That's why foam polyethylene is used a lot. So now, if we look at this, any piece of wire, whether it's coiled or not, has inductance. And what do you see right here between this and this? What is two conductors with a gap in between known as?
Capacitor.
That's a capacitor. Okay, so we have a capacitor and we have an inductor. We have capacitance and inductance that our cable is made of. So what we can actually do with this is model our cable, because this is actually a cylindrical capacitor, if you think of it that way, that it kind of looks like this. And it goes on forever. Essentially, we have a network of capacitors and inductors. The capacitors connecting the points to each other, the inductors separating things out. So what we can do is we can actually take two capacitors in parallel and make them each twice the value, and we can split the inductors like this, and now we have these sections. Notice we have capacitor, inductor, capacitor, capacitor, inductor, capacitor, capacitor, inductor, capacitor. This has an impedance. Each one of those sections has an impedance. And interestingly enough, they tend to cancel each other out. So it has not just an impedance, but a characteristic impedance defined by the size and, more importantly, the ratio of the sizes of the things to each other. That defines something called a characteristic impedance. And it doesn't actually cause loss. Loss is caused by resistance in the conductors. The center conductor, yes.
You had a dropout there for about 5-10 seconds.
Oh, okay. Okay. What did I get?
We didn't all experience that.
Oh, okay.
All right.
Yeah, no
Okay.
dropout here.
Okay.
No,
So,
not here.
okay. So basically what we end up with is a series of networks that go on forever, each with two capacitors and one inductor. Those values are all the same for every one of those little chunks, which basically means that it goes on forever in both directions. And it has a certain impedance measured in the letter Z for each of those sections, which is then known as the characteristic impedance. The losses in a cable are caused by resistance in the conductors. So if I have a cable that has these proportions, so I'm going to draw this. Here we go. Cable with these proportions. And the ratio of the center conductor to the outer conductor and the spacing is such that I have 50 ohms. I could scale that up to where I have this, where the ratios are still the same. And my cable has a characteristic impedance because it's scaled the same way of 50 ohms. Those are both 50 ohm cable. Now, because the losses are largely due to the resistance and not exclusively. I mean, you also have some losses in the cable itself due to length and things like that. But because they're largely due to the resistance in the cable, the resistance in the conductors, which one do you think is going to have higher loss? Which one? The tiny one, because this is going to have tiny conductors, which are going to have a lot of resistive losses. These are going to have big conductors, which are going to have low resistive losses, which basically means that the big cable is a much better cable than the little cable, even though they're both 50 ohms and will both make your system completely happy. So now the question becomes, if I'm going to be sending power through these and I'm going to be running 3 watts, which cable should I use? If the cable's really short, it really doesn't matter. But what if I'm going to be running, if I have an FM radio station and I'm going to be running 30,000 watts, which cable should I pick?
The needed big one.
Right. And that's because of the losses in the cable. That's because of the losses. So when you get to looking at an FM radio station or a digital TV station or something like that, where you might have 30,000 or 50,000 watts, you may actually have, because of the losses, 6-inch wide cable going up the side of the tower. This is known as hardline because you can't bend it. You could have half-inch hardline, you could have 3-inch hardline, you could have 6-inch hardline. Some of these are actually metal pipe, where you have a center conductor running right through the middle of metal pipe. Okay, so now getting a signal into your feed line. Well, the next thing to do is we have to somehow manage to connect our cable to our devices. So we have something called an SMA connector, something called an N connector, something called a UHF connector. So these all have different appearances. And while I bring this up, okay, so there's a few different ones. There's an SMA and a UHF and an N connector. These are the most common ones you will see. SMA is a small connector that comes in male and female varieties, and they're good to a couple of gigahertz without any significant loss. An N connector, you can get male and female. These are typically waterproof because they are gasketed inside, and these are good up to many gigahertz. N connectors are the best connectors you can find, but they're a little bit of a pain to work with. Okay, so a connector called a UHF connector, what frequencies do you think that would be good for?
UHF?
But it's not because UHF in this case stands for universal high frequency. So a UHF connector is actually terrible at UHF. Typically, a UHF connector is commonly known as a PL259, that's the male version, or an SO239, which is the female connector. These are the ones that are most commonly seen on equipment, and these are really good for HF and VHF, but not, oddly enough, for UHF. They're quite bad for UHF. So for UHF, we typically switch over to N connectors or SMA connectors. But it's important to note that PL259s and SO239s are really, really common. Like 99% of equipment comes with those two types of UHF connectors for HF and VHF. Okay, let's see. Next. Go back to this.
How would you waterproof them if they were not already?
You use a lot of electrical tape and self-sealing mastic. And their 3M makes some really good stuff. Probably like there's another one called Coax Seal. It's basically a self-vulcanizing rubber. And you just wrap it and squeeze it down. And I've actually had on the back of that same car that I was talking about, I had a really ugly piece of cable. But when it came time to taking the antenna apart, I used a knife and cut off the mastic that I used to waterproof everything. And it was like the day that I put it in. Even though I'd driven, 125,000 miles with road salt and stuff like that splashing up over it, it works really well. But speaking of which, UHF connectors, which are really common, are not waterproof. So if you're going to use them outside, you're going to wrap them with electrical tape and you're going to use mastic, the self-sealing, self-vulcanizing stuff to waterproof them. Because the most common problem with coaxial cable is that it gets water inside. Wet coaxial cable tends to corrode. Corrosion doesn't carry current very well. And that cable becomes lossy. At that point, you basically throw it away. So there's another thing about this, which is why should coaxial cable be resistant to ultraviolet? If it's not resistant to ultraviolet and it's out in the sun, it dries out, then it cracks. And what gets in through the cracks, everyone?
Moisture.
Water. Yeah. And then you have ruined cable. So you can also have air core cable, which is typically what's used on some of the larger radio and TV stations. Again, hardline. The problem with that is that you have to actually purge all the water out of the air that you're pumping into it. PL259, remember, that's a form of what kind of connector? Everybody remember what that's called?
UHF.
A UHF connector, which is terrible for use on UHF. That's right. That's right. And in fact, the next question is the following connector types most suitable for use above 400 megahertz. 400 megahertz falls in the UHF band, and your choice is an N. N connectors are great for that. Again, kind of a pain to work with, but they work very well. Okay, so now we're into SWR. Notice they just threw SWR in here. SWR is standing wave ratio, which I believe is covered right here. Yes, in the very next section. SWR is a measure of how well matched something is to something else. And this can be caused by a loose connection in the antenna or feed line. It can also be caused by an open circuit or a short circuit or just a simple mismatch. So what we're going to cover now is standing wave ratio. So if everybody can picture, and I don't know if anyone's ever done this before, but let's say for fun, and you could do this tonight if you feel like it, you take a jump rope and you tie your jump rope to a doorknob. You tie the end of the jump rope to a doorknob, and you pull the rope tight, and then you whip the rope, and you keep it tight. What will happen is you will form a wave which will travel down and eventually get down to here. What will happen when it gets to the doorknob if the door is closed tightly?
Jerk.
Yeah. And what will happen to the wave?
It'll reflect.
It will bounce back. That is a poor match. That is the easiest analogy I can come up with to think of a bad match. Now, let's say that I managed to get an infinitely long jump rope, which somewhere out in the ether, could be 1 billion miles away, and I managed to somehow keep it taut, and I put a wave by whipping the jump rope onto the jump rope. What will happen to the wave?
It'll just keep going that direction.
Will I ever see it again?
Nope.
I will never see it again. That's exactly right. So this is known, that's a perfect match. In other words, that cable goes on forever. Now, if, for instance, I took away the doorknob right here, the cable or the jump rope would actually whip by the time it got to the end. And even if I left it open, it would still, have a lot of energy, and it would have to get rid of it somewhere. That could be smacking into the ground or whatever. With this infinitely long jump rope, that energy goes out and it continually gets passed along. This is equivalent to a coaxial cable that is 50 ohms with my transmitter that is 50 ohms impedance, putting power into the cable, which then goes into an infinitely long cable. And if the cable is perfectly matched with the same impedance and it goes on forever, the power will go out and I will never see it again. As far as I'm concerned, I sent it out and it's out in the world. So now what I'm going to do is replace this with something of the same impedance, which I'm going to put at the end, which is a resistor, which is a 50 ohm resistive resistor, which is perfectly matched to the cable. But let's say I don't know that that's out there. That's just behind a wall. I send out the signal. I send out my energy. My impedance is 50 ohms. It goes into the 50 ohm transmission line, coaxial cable, and it goes behind the wall, and I never see it again. I don't know what's behind the wall, but I never see it again. In my mind, what happened to it?
just kept going.
It kept going.
The
It went
road
out.
goes on forever.
Yeah. Or it went out somewhere. And as far as I'm concerned, I never saw it again. I'm happy. You know, it obviously went and did something. This is a perfect match. If I never see it come back. Standing wave ratio, there's a formula for standing wave ratio where I have energy going forward and energy coming backward. If I can measure the energy going forward and coming backward, I can figure out how good or bad of a match this is. Let's say that this is actually, I'm going to get rid of that wall. Let's say that this is a short circuit. What's going to happen to all the energy that goes out?
It's coming, all of it's coming back.
All of it's coming back. What happens if I make this an open circuit?
Still coming back.
It's still coming back because that energy has to go somewhere and it can't go into space because there's nothing to send it into space. So either way, it's coming back. So this has a standing wave ratio, which is the energy coming back of infinity. There's a formula for it, but basically this is an infinite standing wave ratio. It basically means that all of the energy going out is coming back. If I were to put a perfect load on here, that's 50 ohms. My standing wave ratio would be known as 1 to 1. The calculation for standing wave ratio says that that's a 1 to 1 ratio. That's a perfect match. Anywhere else in between is determined by the load impedance. So if this was 100 ohms or 25 ohms, I take the ratio of one to the other and I make it a greater than 1 number. So 100 divided by 50 is 2. 50, we'll take the second one, divided by 25 is also 2. So I take the bigger one divided by the smaller one. Each of these would give me a 2 to 1 SWR. Now, the question is, if I don't know what's actually out here, do I know which one it is, whether it's 100 or 25 ohms?
Nope.
Nope, I don't. All I know is that I have energy coming back. And unless I have something that goes out and actually gives me a calculation of the impedance out there, and there are such things, this is known as an antenna analyzer. Then I don't know which one it is, and I don't know how to fix things. So having a tool like an antenna analyzer helps you to fix problems like that.
You could try making a change and then just see which way it goes.
That's true too. But only if you know what difference the change makes. So here's a question. So let's say that I have an antenna which I have cut for a certain length, and I get an impedance of an SWR of 2 to 1. Do I know if it's 100 ohms or 25 ohms? I don't. It could be either one. Now, the question really is, how do I know what to do if I only have that little snippet of information other than trial and error? And the answer is I don't. However, if I have an antenna analyzer and it's a graphing analyzer, and here's the frequency of interest, and here's my SWR plot, and it says that it looks like this. And this is 0 frequency, and this is infinity frequency. So obviously the SWR dips below my frequency of interest. What does that mean about the antenna?
Not ideal.
It's not ideal. And what should I do with it? Which way should I go? If you think about if you play a musical instrument and you think about like a tuning fork or or an organ pipe, how do you make the frequency higher?
Make it shorter.
You make it shorter. So what would I do with my antenna?
Make it short.
I'd clip a little bit off the end and try it again. And now maybe it looks like this. And now we're a little bit closer. And why do you always start on the low side of the frequency? Why do you always make antennas a little longer than you think you need to?
Because it's easier to subtract than to add.
It's easier to cut stuff off than to put it back on. That's exactly right. Okay. That's exactly right. Okay. A reading of 4-1 is a really, is what they call an impedance mismatch. Basically, if it's anything other than 1-1, it's a mismatch. A 4-1 basically indicates a significant mismatch. And what ends up happening at that point is that, let's say that you have a transistor output in your radio. And here's your transistor. And your transistor output is designed to operate at a voltage of 36 volts DC. And a signal goes out and it has a peak of 36 volts. And it hits a mismatch out here as it's traveling outward, and some signal is coming back, and it's coming back out of phase because you can't predict these things. Well, it comes back into the transistor. And right here, for instance, you have 26 volts, and coming back, you have 16 volts. They add together because you couldn't predict that this was going to happen. And what is your total voltage if you have 26 and 16 there?
42.
What happens to your transistor?
Circuit shut down.
Well,
or reduced power.
If you are lucky, then you get
It gets
something
hot.
called, if you are lucky, you get something called foldback, which is that the radio senses what's happening and says, I need to knock down my output power before I toast something. If your foldback circuit doesn't work fast enough, what happens to your transistor?
It melts.
Yeah, you
Pop.
basically go pow, and you're on the hook for a couple new transistors, and they'll probably cost you on a handheld radio. You basically end up, if it's a cheap radio, you throw it away. if it's a $500 radio, you either get some replacement transistors and solder them in, or have somebody do it for you. Because, you know, basically once a transistor's dead, you've let the smoke out, it's never going to work again. So foldback is what a solid state, which is a transistor amplifier, does to protect itself from damage from high SWR. This is why, for instance, I have an ICOM 7300 radio, which has something called emergency mode, which basically says that in case of high SWR, if I really need to transmit at higher power, I might kill my radio, but if I put it in emergency mode, it's going to let me do it because it's an emergency. Normally,
Into the world.
Yep. Normally it would shut it down and keep the power down. Okay. So power lost in a feed line turns into heat. Here's the output power reduction. And again, to protect the output amplifier. Let's see, what should be considered when selecting an accessory standing wave ratio meter? Well, they're usually designed for a particular frequency range and power level. If you take an SWR meter that's rated for 200 watts and you run a kilowatt through it, you'll probably end up frying something. You can use a directional watt meter and plug those values for forward and reflected power in and get your standing wave ratio from that. An RF power meter goes between the transmitter and the antenna somewhere. So here's a question. So now we're talking about antenna analyzers. So an antenna analyzer will tell you what your antenna looks like at frequencies other than the one you intend to look at. So the question is, how does an antenna analyzer achieve this? How does it transmit at 13 megahertz? That's not a ham band. What do you think? We were kind of talking.
Variable attenuator.
no, we were kind of talking about it yesterday a little bit. All those wall warts that you've got, all those remote controls and things that generate a little bit of energy. This is a part 15 transmitter. It's about a 1 milliwatt transmitter. That's very, very sensitive. That's a very sensitive receiver, but because it's an unlicensed device, it transmits so little power that it doesn't have to be licensed. So it allows you to actually test an antenna outside of the ham bands, which is why an antenna analyzer is a very useful device. An antenna tuner. We drew this yesterday. We're going to draw it. Actually, yeah, we did draw it yesterday. We're going to draw it again. Frequency dependent components. Remember we drew this? But now we're hooking it up to an antenna, and now we're hooking it up to a radio. What impedance does the radio look for, everyone? How many ohms?
50.
50 ohms. Our antenna is how many ohms? Question. Well, I don't know. It's not, if it were 50, we wouldn't have a problem, right? So we have mystery antenna. So this has an impedance of I 2 pi FL, or sorry, that's this one down here. This one has an impedance of minus I over 2 pi FC. This one has an impedance of minus I over 2 pi FC. And these allow us to take this mystery antenna, which has an impedance of R plus IX, and do this with it. Whoop. Cancel out the I part, which is the imaginary part, so that it is purely resistive. Magic. Absolute magic. Makes it a resistive device. Now,
Hey,
the question
Scott,
is, yeah,
is that negative I on both of those?
yeah, because they're
Okay.
capacitors.
I thought so. I just wanted to
Yeah,
be
they're
sure.
capacitors. But now here's the question that I have for you. Does that solve the problem of your antenna?
No.
Nope, doesn't. Now, what does it do?
Protects the radio.
Makes your radio happy, right? But it doesn't solve the fact that you've maybe got a mismatch up here, which is causing power to go up and down and up and down, because every time it gets to a point where it doesn't match properly, it gets reflected back. So if you have a really bad SWR, let's say you have a 10-to-1 mismatch here at the antenna, you might be able to tune it. You might be able to actually use the radio, but depending on how lossy your coax is, how lossy your feed line is, for every 100 watts that go out, so for every 100 watts that get put out there, you might actually get like 5 watts out if it's really bad. And where's the other 95 watts going?
Heat.
And where's the heat going to be dissipated?
Mostly in the capacitors in the coil.
Actually, mostly right here in the feed line. There's a little bit in here, and a little bit in here, and a little bit in here, but a lot of it in here. So it's just basically going to warm up your cable, because you have signals that are continually going up and down and up and down and up and down. And every time they hit a mismatch, well, you now actually have a mismatch right here. So it's 50 ohm cable, and now you have all that energy circulating back and forth inside that cable and in the tuner. So yeah, that's why it's better to have an antenna that's matched properly. If you can't do that, then really what you're down to is getting really, really low loss cable to account for that. And of course that that basically requires some engineering to figure out what it's going to be. Okay. The primary function of a dummy load is a 50 ohm resistive load. Notice it's resistive. It has an impedance of 50 ohms, purely resistive, to simulate a perfect antenna. so that all your power that's going out gets burned up as heat, simulating what an antenna would do, except burning it up as heat instead of sending it off into space. So that allows you to basically test your transmitter completely off the air. And why is a dummy load a non-inductive resistor?
Because you'll generate radio waves if you've got an inductor in there.
Well, it will maybe a little bit, but here's a more important question. If it's not, if let's say it's an inductive resistor, sometimes a resistor is built like this. Inside a brick of ceramic material, you have this. Because I mean, you can put more wire in a coil than in a straight line, right? If you coil it up, right, you can wind it around a bunch of times and you can put a lot of wire in there. But this has inductance. And it has resistance. So what is its impedance? R plus IX. So here's your R, here's your x-axis. And what is the impedance, or what is the reactance of a coil? Okay, does anybody see a problem in that number right there? There's one term in there that is going to be very problematic.
Frequency?
Frequency. Because what does that mean if the frequency is 0? What's my x?
0.
0. What if my frequency is 100? Equals 200 pi times L. If my frequency is 200, my reactance is 400 pi L. If I draw this on a graph, I have a resistance of 50 ohms resistive, but then I have a reactance which is going to go up, but depending on the frequency, it goes up a different amount, doesn't it? Well, that's not really 50 ohms anymore, because at one frequency it's here, at another frequency it's here, at another frequency it's here. So this might be 60 ohms, this might be 70, and this might be 90. And what is my device supposed to be? How many ohms?
50.
50. The only way to do that is to eliminate the inductor completely. And the way to do that is to not build it like that. That's why when you buy a dummy load, it is not built like that. That's why the answer is a non-inductive resistor. Okay. How about a 5-minute break? Because the next part of it is amateur radio signals, which is totally different.
Sounds good.
Sounds good?
Okay.
Okay. 5-minute break. Could anyone hear that okay?
Yes.
Okay, good. That means that it's working. All right.
Yep.
Questions before we move on?
That said Voice of Korea on one section of that. Was that North Korea, like Voice of America type stuff?
No, actually that was no, it was a Russian calling CQDX. Just a Russian calling CQDX.
Nice.
Okay, so what we're going to do now is something called modulation. So being able to generate a sine wave is no big deal. So what we're going to do now is we're going to have to start thinking about waves and stuff a little bit differently. We're going to have to start thinking about things by frequency. So a wave that looks like this has a couple of different characteristics. It has one, which is how far offset it is from something else. This is known as its phase. It also has its size, which is its amplitude. And it has a frequency. Those are three fundamental characteristics of any sine wave. So in order to put information on a wave, right? So I'm just going to draw a single wave here. What information is in this wave? The answer is basically nothing other than it exists. So in order to make it have some other information, there's a couple things I can do. I can make it bigger and smaller. That would be amplitude modulation. I'm changing it to make it bigger and smaller. I can change the frequency. And I can do that based on some algorithm. I can change the frequency. I can also change the phase. I can suddenly have a jump to here. And I can get up to here and suddenly have a jump to here. That sudden jump in phase indicates that something has happened. So I can change frequency, I can change amplitude, I can change phase. Most VHF and UHF radios either use frequency modulation or phase modulation. Okay, let's share. Okay. Most FM radios on VHF and UHF are actually either frequency modulation or phase modulation. Phase modulation can be very similar to FM. Packet radio is basically digital communications over frequency or phase modulation. That's what packet is. If anybody wants to listen to what packet sounds like, you can tune in to 144.39 if you have a handheld and listen to packet. That's kind of the national packet frequency. That's 144.39. It'll sound like little bursts of digital communication. Amplitude modulation is basically taking a signal like this and making it louder and quieter, louder and quieter, and louder and quieter based on something that's happening. If I speak louder into the microphone, it'll make the signal bigger. Single sideband. Okay, so now we're going to have to start thinking about what we can do to different waves and what they actually look like on the frequency band. So remember that frequency band goes from 0 hertz all the way up to infinity hertz. So we could draw this entire map. There's a lot of stuff in there, but instead what we're going to do is we're going to pick a single frequency of interest, which we're going to call our center frequency, which is in a band that we're interested in. And we're going to call this F. That's our center frequency. Put a little letter C after it for center frequency. That's our frequency of interest. When we make a sine wave, that has a frequency of FC, it will appear as a spike right there. In other words, it is purely at that frequency. It is nowhere else. Now, another thing we can do is we can take that frequency and we can modify it. Well, if we make it a lower frequency, if we take that frequency and add a lower frequency to it, we can get something over here. If we take that frequency and make a higher frequency, we can do something over here. The amount of change that we get in this frequency is known as the deviation, which is literally deviation from the center frequency. Most FM has a deviation of 5 kilohertz, plus or minus 5 kilohertz. So when you talk into an FM radio, it basically takes that center frequency and causes it to be sprayed plus and minus 5 kilohertz from the center. When it gets to the other side, having been transmitted, there's something called a discriminator, which basically does the decoding. And if anyone's curious, this is known as the act of putting information on a signal is known as modulation. Now, we also have something called demodulation, which is taking information out of a signal. If anyone has ever heard of a modem, this is a modulator demodulator. We just call that a modem. Okay, so we basically have we have a balance modulator, or it essentially causes deviation, and then we have a discriminator on the other end, which allows you to get information back out of the signal. So that's for FM. If we were to take AM, we still have our center frequency. This is amplitude modulation. We would basically do this, and a copy of our voice would basically take up the lower part and the upper part. This center frequency is known as the carrier frequency, or FC. And as energy is used to generate those sidebands, as they're called, the carrier drops. Sorry. The carrier drops in amplitude. As it turns out, it doesn't have any real information in it anyway, other than where the stuff is. This is called the upper sideband, and this is called the lower sideband, because this is on the upper side of the frequency, and this is on the lower side. Now, the interesting thing is that on the frequency spectrum, it turns out that these are exactly mirror images of each other, which means that they are just duplicates. They have the exact same information, which means that if we could be really clever before we put this into the amplifier, what we could do is we could say, well, since they're duplicates of each other, if we only transmitted one half of it, and we let the other, and we let the receiver put the carrier back in, well, then we could save all of that power that we're using and just use it on transmitting information. This is known as single sideband. This is the most commonly used mode of voice communications on the high frequency bands. We either choose the lower sideband or the upper sideband, depending on our choice of modes. Typically, the dividing line is at 10 megahertz. Below 10 megahertz, we use lower sideband. Above 10 megahertz, we use upper sideband. But fundamentally, they are essentially the same. They work the same way. Okay. So what is the advantage of using one mode of modulation compared to another? Single sideband takes up about 3,000 hertz of space. Bandwidth is a valuable resource. The reason I say it's a valuable resource is because once it's being used by somebody, it can't be used by somebody else. Amplitude modulation, because it has both sidebands, takes up about 6 kilohertz, 6,000 hertz. FM takes up between 10 and 15,000 hertz. That's a lot of space we were to physically draw that on the band, we would see that. So here's our center frequency. Our single sideband, we'll go with upper sideband, is about 3,000 hertz. AM would be 6,000. FM would be about 15,000. If we were trying to put multiple signals on a band, we obviously would go with the modulation technique that is narrower, if it can still carry the information. So why do people do digital communications? Because a signal such as PSK31 takes up 31 hertz of space, not 31 kilohertz, 31 hertz. You can put almost 100 signals inside the same space that you can put one voice signal. You can do Morse code. Morse code takes up about 150 hertz. You can put 20 of them inside the same space as one voice signal. And when it comes time to figuring out which one you're going to do, your transmitter only has a certain amount of power available. If you have a, let's say your transmitter power is a bucket of water and you want to fill this entire space, you might only be able to fill it that deep. If you were to transmit in a very narrow band, you might be able to fill it that deep. Well, okay, that now goes off into the world. When it gets to the other side, what it finds is that the person who's listening to it has noise that basically keeps anything below here from being heard. Well, this very carefully crafted signal is completely below the noise, whereas this signal right here gets through. And that's why people sometimes will operate using a very narrow bandwidth mode, because you can dump more power into each hertz, into the total bandwidth. This is something known as power spectral density. Typically, the higher this is, the greater the chance you have of being heard on the other end. Okay. FM compared to single sideband, there's a disadvantage for those of you who have used FM. You will probably use FM. I use FM all the time. FM has something called a capture effect. This is why FM is not used on the aircraft frequencies, because only the strongest signal will get heard. On AM or single sideband, you can actually hear multiple signals at the same time. On FM, only the strong one wins, which means that a weak signal in the background might not be heard at all. Okay, AM fast scan TV. This is NTSC television, old school analog TV. Believe it or not, we are allowed to do this. We actually have allocations for this. Now, this actually shows up on these bands. It takes up 6 megahertz, not kilohertz, megahertz of space. So clearly, like the 10-meter band only goes from 28 to 29.7. There's only 1.7 megahertz there. We can't do television there. But notice this amateur TV fast scan, the light blue. At 70 centimeters, we have 420, 426, 430, 432. We actually have room for 2 TV channels there. We can actually do old school fast scan TV. At 900 megahertz, we have enough room for 3. At 23 centimeters, we have enough room for 1, 2, 3, 4, 5 TV channels. And there are groups of hams who do fast scan TV, like old school TV stations, except that they use it to talk to each other, using your standard television cameras and television transmitters. Morse code is also known as CW, or continuous wave. Morse code has a very narrow bandwidth of about 150 hertz. And an electronic keyer, which if you do Morse code, and a keyer is something that allows you to send dits and dahs using Morse code without actually having to key each one individually. It allows you to send strings of dits and dahs. Okay, now we're on to digital modes, packet and PSK31. The digital modes are great because they allow computer to computer communications. If I were to say, let's say using voice, I want you to go to street. Did anyone hear what street that was? Anyone?
No.
I'll do it again. I'd like you to meet me on street. Right?
Oh,
That information is gone. However, if I were to encode my entire message and say, okay, here's the whole message, and I'm going to send it 3 times. And if you get 2 out of 3, you're going to say that they match and that's a valid message. If I were also to take that and type it in to a string and take that string and turn it into ones and zeros and then say, okay, you're going to take a total count of all the ones and zeros and figure out how many ones there are and how many zeros there are. And if there's an error, you'll have enough that you can make corrections for at least 2 letters. There's a good chance you might be able to figure out what it was. That is what digital communications allows us to do versus analog communications. On analog, if the signal is lost, it is lost. In digital communications, we basically have redundancy that allows us to use ones and zeros, which are inherently more immune to noise and information loss, and to be able to add something known as parity, which allows us to do like a check after the fact to see if what was sent was really there. So digital communications modes, we have packet, we have IEEE 802.11, which is another fancy word for Wi-Fi. And we also have this thing called FT8. FT8 is a weak signal long distance communications mode that's used for a lot of different things, including generation of that world map that I showed you. Packet radio, there's a checksum that permits error detection. That's basically saying, did I get enough ones and zeros to know that this is a valid message? There's a header that has, okay, the message is going to Eileen. Well, if it ends up in Claude's mailbox, you know that something was wrong, right? So if it ends up in the wrong place, it gets rejected. So there's automatic header information that's sent with it. And if something comes in that's just garbage, and it says, look, you know what? I'm the receiving station. I'm connected to a computer. The computer program says I can't understand any of this. It sends a message back that says, please send it again. So it handles a lot of the corrections that normally would be done by people. ARQ is basically that correction system saying, look, I lost it, send it again. APRS, this is the automated packet reporting system. APRS is an application of packet radio. Can everybody see that? That map up there?
Yes.
Yep.
yes.
Okay, so this is either handheld radios or mobile radios, or it could be base station radios connected with a computer, connected with GPS that are beaconing out information on, again, that 144.39 frequency, which is kind of like the global packet radio frequency, sending out either weather information or vehicle information, speed, direction. We use it for tracking balloons. We can use it for tracking assets like, let's say that let's say that we have a road race. We can put a tracker on a vehicle and we know where it is at all times. We know how fast it's been moving. And what's cool about it is that it doesn't require a cell phone to do so. We can basically know where it is because if its beacons are picked up by any other radio in the network, they will forward it. And eventually it will make it to this site in Finland and be placed on this map. We then can zoom in on something and say W7ZJL-9, 8 miles an hour at this altitude, at this heading. So it's a very interesting melding of technologies. Okay, so that's APRS. GPS, text information, weather data. PSK is phase shift keying. It's another form of modulation. that allows you to send information. There's that mode called PSK31. It's a digital mode, which means it's computer to computer. 31 hertz, very, very narrow bandwidth, and it worked extremely well. DMR is digital mobile radio. So a typical frequency channel on a repeater is 12.5 kilohertz wide, or 12,500 hertz. DMR is a digital technique by which normally your voice would fill up an entire space. It time multiplexes and says that group A has these time slots and group B has these time slots, and all the radios, all the people that are dialed into group A will use the channel only during that time, and group B will use the channel only during that time. And there's enough information being sent during that time that their radio can actually not blank out, and it'll sound like there are two completely independent conversations going on just one frequency. And neither group knows that the other one's there. So it's a very good way of getting more use out of a busy frequency. So that, again, that's DMR, which stands for Digital Mobile Radio. WSJT is a software package that supports this thing called FT8. FT8 you will probably hear about more. It's used around the world. Again, it's the source of all the information for that map that I brought up with pictures from, propagation from all over the world. It also has a whole bunch of other modes that are part of it, which allow you to do meteor scatter, moon bounce. Yes, we do bounce signals off the moon. There are also some hams that have done Venus bounce, which is a little more challenging because it's a lot further away, as well as meteor scatter. Those are all different types of communications that require different speeds, and WSJTX supports them all. The biggest one, of course, that everybody uses is FT8. A mesh network is a self-healing computer radio network that basically figures out from point to point whether or not a communication is possible at very, very high data rates using Wi-Fi equipment, believe it or not. Older Wi-Fi equipment, if you modify the firmware because of the frequencies it's on, turns into a ham radio. We share a lot of those frequencies. What we have is we have much higher power limits than they do, and we also can hook it up to any antenna we want, and we can run really high bandwidth to the point where we can actually create a network that rivals the internet, except that it's completely radio based. And then between that network and the internet, you can have a gateway, so you can send email over the radio and it goes over the internet and ends up wherever you want it to. But it's a self-healing network as well. So if a node goes down, for instance, you lose power, the messages find another way to get there. Okay, station safety. This is extremely important. What health hazard is presented by electrical current flowing through the body? Well, we are electrical things. We are electrical beings. We have nerves that run the entire length of our body. We have an electrically powered heart. Everything in every cell is an electrical thing. There are electric potentials that allow our cells to get oxygen and to feed and to use energy. And if you get a shock, it can basically keep these cells from functioning. It can heat up your tissue, just basically like, has anyone ever seen a hot dogger? Anyone ever seen the thing called a hot dogger? Where you stick, remember those? You stick an electrical probe in both ends and it cooks the hot dog from the inside.
Oof, no.
Yes, yes. That's called a hot dogger. I don't think they sell them anymore because they ended up tasting kind of metallic. But they were kind of unsafe.
Or like a stinger. Remember a stinger where you could heat up your water?
Yeah, something like that. Except this is literally for cooking a hot dog from the inside. Electrical current can do that to you as well if you get a shock. So it can also cause involuntary muscle contraction, which can stop your heart. Black wire in a 3-wire 120 volt cable. 120 volts is your wall power. Again, you have 3 wires in there. You have black, which is hot, white, which is neutral, green is ground. The black wire is always hot. How do you guard against shock? You ground everything. Ground, 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 ground. Mechanical interlocks on high voltage circuits. So where would we encounter high voltage circuits? Some people still use tube amplifiers. In order to make a tube amplifier work, very often the plate voltage is on the order of 3,000 volts DC. That can really ruin your day. So if you open the lid to look inside the amplifier, there's usually an interlock switch that you put in there so that it keeps the voltage from being active.
Or an auto flyback on a TV.
That'll work too. Yeah, that's 20,000 volts. Although that's a tube TV, and I don't know if you're going to find too many of those anymore. And I've seen the zap when you stick the screwdriver underneath the boot on a TV tube. And you know, a TV tube can, because it's a big capacitor, can hold that 20,000 volts for years without dissipating. So don't assume that just because a TV is 10 years old and you're trying to get rid of it by taking it apart, that it doesn't have voltage on it. Again, can really ruin your day. The purpose of a fuse in an electrical circuit is to remove power in case of overload. We covered that ad nauseum yesterday. If you're building your own equipment, then you put a 120 volt fuse in the hot conductor circuit. So in series in the hot conductor. Why would you never replace a 5 amp fuse with a 20 amp fuse? Because you might let excessive current through, and that could burn your house down. Inside a power supply to filter out AC typically has a really big capacitor. Really big capacitor does a great job at smoothing your ripple, but it also charges up, and unless there's a bleeder resistor across it, it can maintain that charge for a very long time. So you stick your finger into a power supply, you manage to find the hot lead on a capacitor, you might get a shock from that.
They kind of gloss over it, but on the putting it in the hot wire, the switch, a fuse on the hot wire. If you put it on the ground wire, it will work most of the time.
Yeah.
But it's a real hazard for if you touch that hot wire while it's plugged in.
That's right. And just because the ground wire or the neutral trips doesn't mean you're not going to get a shock. I mean, if you're standing in a pool of water, you're going to get a shock. And that's actually why we use something called a GFCI as well. What hazard is caused by charging or discharging a battery too quickly? In particular, a car battery. Car battery chemistry is sulfuric acid and lead. That particular chemistry, when you discharge it or charge it, can generate hydrogen gas, which can tend to be vented if the pressure gets too high. And then you come along to your discharged battery and you hook up a fresh battery to it to give yourself a jump start, and you generate a spark in a cloud of hydrogen. And what does that do?
Explosion.
Everyone remembers the Hindenburg, right?
Yep.
Yeah. Yeah. And of course, it's not just the hydrogen explosion, but very often the explosion will take out a part of the battery. And what's inside a car battery?
Acid.
Sulfuric acid, right? So now you not only have an explosion, but then you get a bath in sulfuric acid. So be very careful. Antenna and tower safety. When putting up an antenna tower, make sure you don't touch any overhead wires. You have to stay at least 10 feet from any power lines if anything falls or anything moves. And just last year, there was a very, very experienced antenna builder and contester and DXer who was out at one of his friends' places. They were doing a big antenna party on a big piece of property, and they were lowering an antenna down, and it got caught up on one of the guy wires, and he went over to move it to make sure it didn't get caught. The other end of the antenna was touching a power line, and he died. This and I mean, this is someone with a lot of experience. That's why whenever you're working on something like that, it seems silly to have somebody who's just standing there looking and watching, but that person's job is to just stay completely detached from what you're doing so that when you forget what you're doing, they can stop you from killing yourself. Let's see, why should you avoid attaching an antenna to a utility pole? First of all, unless it's your utility pole, you don't own it. You also don't know how much voltage is up there. Does anyone know what the approximate voltage is in residential utility lines running overhead?
10,000?
How much?
About 10,000?
Yeah, about 10,000 volts. That's right. And the reason
Isn't it the amperage that kills you, not the voltage?
No, it's the voltage that kills you.
Okay.
The voltage kills you by making current flow through your body. So yes, it's the amperage that kills you, but a 9-volt battery won't kill you. Whereas, 10,000 volts will generate a significant amount of amperage driving through you.
Gotcha. Okay.
Yeah. Now, interestingly, let's say that you're working on, let's say that you're a high voltage tower climber, or you work on 700,000 volt lines. You can work on them hot. If you work on the danger is that once you're at voltage, you have to make sure that you don't touch anything else at any other voltage. So the people who work up there, the really high voltage linemen, they have completely fiber optic booms, but everything else that they're using is ungrounded, like metal cage, metal tools with no insulation. And the first thing they do when they get up there is they throw a clamp up on the power line so that the entire assembly on the boom, including them, is at the same voltage. Because if you never find a different voltage, you'll be okay. That's why birds can sit on a power line and not get electrocuted.
That's why eagles do get electrocuted.
That's why California condors became became endangered in California, because the power lines were close enough together that when they spread their wings, they would touch two lines and get electrocuted. So the solution for that was moving lines further apart so they didn't get electrocuted. Let's see, hazard caused by touching an antenna is an RF burn to the skin. I've got one that I think has healed, but it makes a tiny little blackish brown burn mark and it goes inward, which is very, very painful. When you're climbing an antenna tower, make sure you're wearing an approved harness, use appropriate tie off, and never, ever, 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 ever go up by yourself. If you have a heart attack or you get stung by a bee and have a reaction, or something happens and you get hung up and there's nobody there to help you, or let's say you're wearing a harness and you fall and you get caught and you're left hanging there for 2 hours, you're probably going to die. Even if you didn't hit the ground, your circulation's going to get cut off and you're probably going to die. So always, always, always have somebody out there if you're climbing. If you're doing a crank up tower, make sure you don't climb it when it's fully extended, unless you have mechanical safety locking devices installed, or make sure it's retracted. A turnbuckle is something that basically allows you to tension a guy wire or guy rope. These, because of wind, will tend to vibrate. When they vibrate, they of course tend to loosen, which can make your guy line slack, which can cause a tower to crash to the ground. So we have something called a safety wire, which goes through the open part of a turnbuckle, which keeps it from loosening up. Grounding requirements are for towers are governed by your local electrical codes. The big decider on those starts with the National Electric Code, or NEC. If you live in a state, which most of us do, you might have state codes, you have local codes, county codes, city codes. Everything has to be grounded to whatever your local code says. Just good practice. If you have a like a 3-leg tower. Each leg of the tower gets a separate ground rod, and it's 8 feet long, going straight into the ground and to each other. You want to give lightning as good a chance as you can to go into the ground and away from you. Why should you never solder anything on a ground rod? What do you think?
Connection.
Oh no, it's a great connection.
Okay.
Why would you never solder?
Melt.
Yeah, as soon as you get a lightning strike, that solder is going to melt.
Oh,
That's why we either bolt it or we use something like CAD weld and actually, weld it in place, because solder will melt very quickly. Good practice when installing ground wires on a tower: short and direct. Avoid bends. Lightning likes to go around curves and in straight lines. If it encounters an elbow, for instance, it will just simply jump out to the ground. And it won't have a very good path. It'll try to jump to the ground, but some of it will end up probably where you don't want it to. External ground rods could be grounded together with a heavy wire or conductive strap. Lightning arresters. Okay, a lightning arrestor goes in your line itself, like in your cable, and it connects the center conductor of the cable to ground. Now, you would think that that would be a bad thing, right? Because if I have power, which is normally going out to my antenna through the center conductor, and I put something in there that goes like this, that is tied to the center conductor and goes to ground, you would think that that would be a problem, right? Well, actually, the way that this is built internally is that that center conductor kind of goes like this, and it goes through a gas-filled tube. And the gas is usually nitrogen or something like that, or argon, so that only when the voltage in there gets to, let's say, 3,000 volts, like a lightning strike, that's when it ionizes the gas and gives you a path to ground. And that's how a lightning arrestor works.
Cool.
Yeah.
Good. I'm agreeing.
Oh, good.
I've got a lightning arrestor, and I wondered why that screw was on the top, and did that need to be grounded or not?
Oh yeah. Yeah. I mean, that's your that screw, that lug is your path to ground.
Okay.
Otherwise, it'll just go right through it. And that's why a good lightning arrestor will also have a replaceable tube, because once it's been used, it's pretty done. So, RF hazards and radiation exposure. Radio signals are low energy compared to X-rays, for instance. X-rays and ultraviolet radiation, they cause damage to cells. They are known as ionizing radiation. Ionizing radiation, again, they can rip electrons off from where they used to be. That's why we like them in the atmosphere. That's why we don't like them at the surface of the Earth. Radio waves are non-ionizing, which means that the only thing that they can really do is they can cause heating. They can't cause cellular damage. Who is responsible for ensuring that no person exposed to RF energy above the FCC exposure limits? That would be the station licensee. In other words, my station in my garage, it is my responsibility to make sure that I don't blast anybody with tons of RF radiation. That's my job. And actually, whenever you build a station, whether in a car or mobile or a station or whatever, you actually have to do an RF exposure evaluation on that station. So there are a couple of ways to do it. Well, you can do computer modeling. You can actually walk around and take field strength measurements, or the easy way to do it, there is something called FCC OET Bulletin 65, which is essentially a calculator. Now, the calculator that the FCC provides is not simple, but I can go to HintLink, I believe, which is a great site. Exposure. Let's see if it's active. Enter parameters. Here we go. HintLink. Okay, RF exposure calculator. Notice it was updated in 2021. It's relatively recent. This basically says This program uses the formulas in FCC OET bulletin number 65 to estimate power density in the main lobe of an antenna. So what this basically is a web-based calculator for doing your safety exposure limits. So let's say I have average power at the antenna, 100 watts. Okay, notice the antenna gain. Now, this is interesting because dBd is compared to a dipole. dBi is isotropic radiator, which is an antenna that sends out energy equally in all directions, which actually doesn't exist. So a dipole is actually 2.2 dB better than an isotropic radiator. So that's how the FCC does it. So we're just going to say we have a dipole, so we're 2.2 dB. We're 5 meters away, and we're at 21.2 megahertz. Am I safe? Yes or no? Well, here are the limits. If it's a controlled environment, that means that I have control over the environment. Maybe I put up signs or a fence that says, don't touch, don't enter. If it's an uncontrolled environment, that means that anybody could just walk by not knowing what I'm doing. You know, it could just be like walking out on the street. So here's my distance to compliance, signal strengths and everything. And you would take this and perform this test, perform this evaluation, and post it on your wall or just keep it in your records. So whenever you buy something new, if it's a significant change, a new antenna, replacing feed line, you should really go back and do it again. You know, you buy an amplifier, you should go and definitely do it again. So when looking at that duty cycle, this is the percentage of time that you actually transmit. So if I transmit 100 watts, but only 10% of the time, my duty cycle is 10%, which means that my average power out is only 10 watts. It's 10% of that 100 watts. If I transmit 100 watts 50% of the time, that means that my average power is 50 watts. That goes into my calculation. Why do we do that? Because it affects the average exposure to radiation. If I drop from 100% to 50% duty cycle, it increases by a factor of 2. I can actually change my allowable power limit by a factor of 2 because my duty cycle went down. Exposure limits vary with frequency because the human body absorbs energy at some frequencies better than others. We have the highest absorption and thus the lowest permissible radiation at 50 megahertz. That just happens to be a sweet spot for most people. So 50 megahertz is the bad spot. What factors affect the RF exposure of people near an antenna? Okay, frequency, power level, distance, radiation pattern, they're all in there. If you have a beam antenna pointed right at somebody, probably a lot less safe than a beam antenna pointed away from them. So what can you do? You can relocate antennas. You can also say, okay, I'm only going to transmit between the hours of 5 a.m. and 6 a.m. I don't know why you would do that, but you could. To stay in compliance with regulations, anytime you change anything, you go and get something new. You go and redo an evaluation. Okay, so setup and operating controls. Operating controls, you know what? We're going to get to that tomorrow. Station equipment. Okay. So I think that's it for today. Is that enough for one day?
Yes.
Thank you very, very much.
Congratulations.
Yeah, thanks.
Thank you.
Thank you so much.
Congratulations. You're 2/3 of the way through.
All